now. So if you have
I'm
any
just trying.
questions,
I'm just trying to wrap my head around all of the math. It's been a long time.
well, I mean, you can distill most of the math, or you can,
Yeah,
you know,
I know we did. I did a construction project and they used the metric system
mhm.
and took a little while to learn it. But once I got it, it seemed to be so much easier.
Yeah, because everything's in powers of 10.
Everything's in tens.
That's right.
So, and it seems like these logarithms and this scientific notation is the same way. Once I get it, I won't forget it. It'd be
Yeah.
so easy. Yeah.
Yeah. And that's why engineering is all metric system. The whole world is
Mhm.
metric. Now we are actually lucky in a way in the United States because we know both,
Right.
you know.
We just don't use both all the time.
Well, it depends. I mean,
It depends, right? It depends. Yeah, you're
in my
right on
in
what
my
job
in
you're.
my world we do.
Yeah, I guess that's
So,
true. Yeah, yeah.
I can convert from kilopascals to pounds per square inch, and from inches to millimeters, and kilograms to pounds force, and newtons to pounds force, because I do it all the time.
Hmm.
But and especially metric, especially Celsius to Fahrenheit. We I do that constantly.
Yeah.
I
Thank
mean,
goodness for Google or ask
and
Alexa.
and actually, if you just type in, like, the Fahrenheit to Celsius converter, it pops it up on the top line of the search bar.
Yeah.
Like, how much better can you get than that?
No, it almost makes it too easy, though. You don't have to think anymore.
Yeah, well, true.
But that could be a good thing.
Here, like, okay, pounds force to newtons.
There you go.
There you go. You just ask for it and it shows up.
And it's all there.
Yeah. Okay, let's see.
Morning, everybody.
Good morning.
Still for another 2 minutes here.
Yeah. I hope people show up.
All the more for the rest of us.
Yeah. Let's see. Um,
Good morning.
Good morning.
Morning. See if I can make this bigger. Yay, that's better.
Uh, Trying to queue up some of the props that I'm gonna have up today. Makes it a little bit easier.
So Scotts, what's easier, taking the online exam or going and seeing the guy across the river?
You know, it totally depends on you. You know, I mean, there's a little more technical stuff involved with, setting up for a remote exam. I mean, you need, two cameras and but they work
Why
very
do you
well.
need two cameras?
Well, one on the screen, or basically one is the webcam looking at you and the other one looking at the room.
Oh, so they're actually making sure you're not cheating.
Correct.
Oh, okay. Gotcha.
Okay, well, it's 7 o'clock somewhere. It's 7 o'clock in Hawaii. It's 9 o'clock here. It's time to start. I already hit record, so we're recording. I assume some people are a little slow waking up, or they're just completely freaked out and not coming back, but I can't do anything about that. So,
And it's already lunchtime here.
yeah. All right. So, good morning. And I hope everybody got something out of yesterday and not completely frightened away. And what we're going to do first is just ask if anyone has questions from yesterday. And you know what? If it's something that you feel like you just don't really understand, it is important that you do understand. So if you feel like you don't understand it and you want to understand it, you're not the only one. So it's a good time to speak up before we dive into new stuff. If not, that's okay too.
Are we really going to be asked questions about radians and stuff on the exam?
No.
Oh, good.
Have you started to go through the question pool? Have you
No,
started to
I
go
don't
through?
really know exactly which place to go for that because, like, there's just a ton load of, and I don't
Well,
know which one's the
go someplace free, first of all.
right. I mean, it's
You-
fun that
Ham-
YouTube has really good tutorials.
Yeah, but as far as actually taking practice exams, Ham Study is great. The app, that Ham Radio Exam app, did you get the big email that I sent out? I assume with
yeah.
it's got recommendations, but hamstudy.org is a fine place to go. It's free. You can take practice tests, study mode, read questions, etc., 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 etc. And
Oh, okay.
you can
Gotcha.
set an account and go through and keep track of your progress. And
I was looking through there, and then I got sidetracked into looking at all the different stuff to support their website. You know, you sit there, oh, well, buy an antenna from us, and
yeah, they
we'll
make good
support
stuff.
it. And I'll tell you what, the antenna looked like it was pretty nice if you want a 2-meter antenna.
Well, it's funny. The signal stick that they use is ultra flexible, but it's a material that is rigid unless it gets well below freezing, in which case it gets all droopy. And then when the temperature goes back up, it straightens back up.
You say it gets droopy?
It actually gets droopy.
It becomes more flexible.
It becomes more flexible when it's cold. Yep.
Oh, weird. That's too weird.
It is a little weird, but that's the chemistry of that particular alloy. So, okay, well, and is it timbre or timber? And you're muted. So
Either one. Timber.
Well,
I usually go by timber, but timbre is
timbre. Like
we.
Okay.
That's all the French I know, but
Yeah. Okay. Okay. So let's get started. All right. So we're on to this page, which is called Feed Lines and Connectors. So we kind of covered antennas a little bit yesterday. And now that we covered antennas, well, you have to know how to get power into your antenna. Because if you can't get power from your equipment to your antenna, it doesn't do a whole lot of good. So there are a couple of different types of cables that you can use to move power from a transmitter or a receiver and an antenna to go between them. So essentially there's probably more than that, but there's One of the easiest ones to use is something called coaxial cable. And it's called coaxial cable. You've got a center conductor, and then you've got a shield. These are basically the power going out, power going back line. And so one thing that's interesting about this is that notice that it's not balanced. It's not the same geometry for both sides, going out and going back. If you look at it from the end, you have, if you think about it, like minus and plus, or A and B, or out and back. Notice that the geometry is not the same. Well, it's also true that because you have different voltages between the inside and outside, you have electric fields that exist inside the material that separates the center conductor from the outside. And notice that it's symmetric around the circle, but it goes from a small radius to a big radius. So this is known as unbalanced line. Coaxial cable is unbalanced line. So now if we take a look at another one, we can have a wire, and we separate them by a certain distance. This would be like A and this would be B. Well, these are carrying equal currents. You're going out and going back. The density is the same. There's a certain symmetry to it. They're basically spaced a constant distance from each other. This is known as balanced line. And what's interesting about this stuff is that unbalanced line and balanced line are both fine to use. There are some tricks to using each one. The unbalanced line, which is coax, it can be buried. You can get it wet. You can, you can get it wet if you protect the ends and make sure it doesn't crack, and it's UV resistant so that it doesn't crack in the sun, because if UV cracks the cable shield, it cracks the jacket, and then water gets in, then you get water soaked cable. The water corrodes the cable and you have a bad piece of cable. If you have a badly done end on your cable where it connects to something else and water gets in, water destroys the cable and you get a bad piece of cable. So the most important thing to note is that what destroys cable?
Water.
Water. So whatever you do, you try to prevent water from getting in. Unbalanced cable is, again, great because if it is a hermetically sealed jacket, you can bury it. You don't have to worry about it getting wet or running it up the side of a tower or sticking it out in the ring. Now, if you were to feed an antenna with coax, what you might have to do is put a choke on it, which is essentially either a coil of cable. So you'd coil up the cable, or you would take the cable and put what's known as a ferrite on the cable, so that if there's any current flowing on the outside of the cable conductor, you can block it and keep it from getting back into your station. You typically don't have to worry about that with balanced line, because the currents are going to be even because of the geometry. Now, there's another thing that we're going to cover right now, which is known as skin effect. So if we were to take a look at a cross section of a piece of wire, and we ran DC through it, we would see that the current is distributed about evenly throughout that wire. If we were to then take that and put AC through it, what we would find is that the current at the center would be practically zero. And as you get closer to the outside, you get a higher current density. This is called the skin effect, and it's a function of alternating current. The higher the frequency you go, the closer the current gets to running completely at the surface. So at radio frequencies, you basically get into a condition where virtually all of your current is running at the surface of the conductor. So it doesn't really matter what the core is made of. This is why this is why there are conductors known as copper weld. Anyone ever heard of copper weld?
Mm-mm.
So it's basically
Okay.
it's a copper clad steel, but because steel is not a particularly good conductor, but it's really, really strong, what you can do for HF is you can put a layer of copper on top of your steel. You get a nice conductive layer of copper and the strength of steel down the center,
And not as expensive.
and not as expensive as solid copper. And it's stronger than solid copper. Okay, so let's see. Because you have this situation, I'm going to draw a little bit of a trick question. Here's our cable. Here's our coaxial cable. Right? So you have a solid center conductor. And okay, if this is a piece of cable, we have a dielectric here. Dielectric is an insulator. It can be air, it can be polyethylene, it can be any number of different things. How many surfaces are there here to carry current?
3.
There are 3. That's right. This is a kind of a trick question. There's 1, and there's 2, and there's the outside of the shield, which is 3. Because the current at HF and higher frequencies travels close enough to the surface of the conductor that it's basically all at the surface. And because the shield itself is not infinitely thin, you actually have 2 separate currents that can flow on the inside and the outside of that shield conductor. The effect of this is that, okay, if you have current flowing on the inside, number 2, that should match the current flowing in number 1, just equal and opposite. But you could have some current flowing on number 3, which is the outside. And that will eventually connect back to your radio. And if you have some current flowing back on number 3, that is not something that you want. So what you would do in order to kill that is we would take a donut, or well, I guess it's more of a cylinder, a hollow cylinder, of a material called a ferrite. This is it's a ferromagnetic material. It's not a magnet, but it's ferromagnetic material. So iron, nickel, manganese, things like that you would make magnets out of. And what you typically do is you go somewhere and buy it, because it's kind of hard to make this way. Essentially, what it is a combination of powdered metal and glue that's formed into a shape and then baked into a solid. And what happens is that if everybody remembers, a magnetic field makes a current. What does a current make?
Voltage.
Nope. Magnetic field makes a current. Current makes a magnetic field.
Oh, right.
Which means that if you have current flowing on the outside of the conductor, you will have a magnetic field flowing around the outside. Now, if you give this current and this magnetic field a place to basically circulate in a material that tends to heat up when it's exposed to a magnetic field, this ferrite core, as it's called, will tend to get warm. And because it's dissipating the energy that the current is making, it makes the current go away. So that's known as a ferrite choke.
How big does that have to be?
Depends on the frequency you're using, depends on the power level, and depends on the frequency response of the material. Now, I will say that everybody has seen one of these. You may just not know that you have. And I'm going to put one up right in front of my camera right here.
Yep.
This is a ferrite choke. This is designed to keep higher frequencies out of your computer. So if there happens to be anything flowing around the outside, it will get blocked before it goes into the computer. So it's a nice way to take AC at RF frequencies and choke it, literally chokes it off.
So is there a table or anything that you can use so when you go to purchase something like that to add to your cable assembly?
There is. And in fact, here is my favorite company for making ferrites. It's called Ferrite. And if you look at Ferrite, you will see that under products, they have suppression component. Look at all of those different things. Ferrite bead on leads, ferrite beads, through hole. There's all your different, and notice they have different materials. Notice 52, 44, et cetera, et cetera. There are so many, here we go, high broadband frequency. Let's go higher frequency. There are literally dozens of materials that have different frequency responses that you can choose from. So the interesting thing about ferrites also is that not only are they used as a way of choking RF energy from places you don't want, they can also be used as the core of an RF transformer. So remember yesterday I showed that we had this antenna, which was an end-fed antenna that looked like this. And the feed point impedance was about 2200 ohms. But our cable was about 50 ohms. So if you have a 49-to-1 transformer that looks like this, which is a 7-to-1 turns ratio, you can use that right here to match the impedance of the cable to the feed point impedance of the antenna. The ferrite, that ferrite core is usually what you use as the stuff that you wrap your wire around in a donut shape. So you choose your donut shape, you choose the size, you choose the material, and then you wrap the core.
Oh, so you like, it takes the place of the steel laminations they used to use in the old days.
Well, steel laminations are great for certain things. They're great for AC transformers, but they're not good for RF AC transformers. They don't have a frequency response that you necessarily want.
Oh, okay.
So you pick a material that has the frequency response that you want, and it's been engineered, which is why you go back to ferrite and say, okay, what is the material type that I want to use? Okay, let's see. We're going to go back to feed lines and connectors here. Oops, wrong page. And here we go. Okay, feed lines and connectors. Coaxial cable's great because it's easy to install. Impedance we covered yesterday. It's like resistance, but it's opposition of current, opposition to AC current. Impedance is measured in ohms. Most coaxial cable is 50 ohms. Okay, so this is an interesting concept. We think of impedance as the resistance to AC, right? Well, it is, and it kind of is. So let's look at a piece of coaxial cable. It's just, essentially two wires that are spaced by a distance. One of them happens to be a cylinder and the other one is like a little wire, but essentially it's two wires spaced by a distance. Well, what are two pieces of metal that are spaced by a distance? What is that called? That's a capacitor. Okay. So we have a capacitor. This is a capacitor. And every wire, whether it's coiled up or not, serves as what? Piece of wire has inductance. So I can actually draw my conductors like this. Per length, they have a certain capacitance and they have a certain inductance. Well, if I split my capacitor in half, because I can do that, then I get these sections, which it turns out they have a little bit of resistance, but more importantly, what they have is an impedance based on the spacing of the capacitor plates and the inductance per foot or inductance per length. So this has something called a characteristic. So when you see something called a characteristic impedance, that is not something that causes loss, but what it does is it it is literally a characteristic of the transmission line that's carrying power from one point to another. So that, for instance, if this has a 50 ohm characteristic impedance, the radio is designed to transfer power into an impedance that has 50 ohms. This then goes up to an antenna, which hopefully is close to 50 ohms impedance. Well, if you have impedance matches throughout the system, you'll get maximum power transfer from place to place. The coaxial cable has losses, but the losses are all resistive because wire has resistance. So you're going to lose a little bit of power in your cable because of resistive losses. The antenna has a radiation resistance. It kind of actually looks like a resistor to RF, so that when you put power out from your transmitter into that has a characteristic 50 ohm load or 50 ohm impedance through a 50 ohm piece of cable and into a 50 ohm load, which is your antenna, you'll basically get maximum power transfer from point to point. That is the point of all of this. That is the goal of this thing called a transmission line, which is that arrow right there. It's to move RF energy from one point to another. So now if we take a look at that and say, okay, well, what's the difference between a cable that's this big and a cable that's this big if they're proportionally the same? This is 50 ohms and this is 50 ohms. What is the difference between these pieces of cable? Somebody tell me.
One's bigger than the other.
One's way bigger than the other one. Okay, so they're both 50 ohms. If I have a 50 ohm transmitter and I have an antenna that's 50 ohms, that's going to work the same as if I have another system that looks just like that, but with a big fat piece of cable. So what is the difference between the thin cable and the fat cable?
One's got more capacitance than the other.
It does, but it has more inductance too. They're both 50 ohms, which means that they characteristically are exactly the same. How are they different? Considering that the big one is just a scaled up version proportionally of the small one.
I imagine the bigger one can carry more power.
It can because the conductors are bigger.
The smaller one would have more surface area.
No, they're proportionally the same. On the big one, the conductors are big, which means that the resistance in the wire is what?
Less.
Lower, yes. And your power loss in cable comes from resistive loss. So your power loss comes from resistive losses. Well, this has low resistance. This has high resistance because they're small wires. Okay, so which one's going to carry more power?
The bigger one.
The big one. Okay. And more importantly, if I put, let's say, 5 watts, or let's say I put 1 watt into this and 1 watt into this, and neither one is going to fry, which cable is going to be lossier?
The little one.
The little one. And in fact, there is a table out there. There are many tables out there in the world, and I'm going to show you one right now. There we go. Coaxial cable attenuation. All right. So notice what it says. RG174 is teeny tiny cable. 58 is bigger. 8X is bigger. These are all, the 4 on the left-hand side are all 50 ohms. The 2 on the right-hand side are also 50 ohms. RG8 and RG6 and RG11 are 75 ohms. So what does this show? Basically, if we compare RG174 to RG58 at any frequency, you'll see that RG174 is very lossy. And in fact, if we had taken intersection of RG 174 and 50 megahertz, we'll see that we have 6.6 decibels of loss in 100 feet of cable. So just thinking about that, does everybody remember what 3 decibels is? How much
Half.
of your power? That's half. So if we lose 6 decibels, we lose a half. We go down by a half, and then we go down by a half again, and then a little bit more, which means that if we have 1 watt going in, we have about 0.2 of a watt coming out the other end with that cable. If the cable's only 6 inches long, it's probably not a problem. But if it's 100 feet of cable, it's a big deal. Now let's go with that same 50 megahertz and go to RG8X. So 50 megahertz intersects with RG8X. What's our loss?
.2 dB.
Now RG 50 megahertz and
Oh, wrong
2.5.
line.
2.5. All
Yeah.
right. And that's a little less than 3. So that's all. So you'd lose a little less than half your power. So instead of 0.2 of a watt, you might have 0.6 of a watt coming out the other end just by picking a different cable.
So that RG8.8X, is that X like a new number for the old RG8U cable?
It's also known as Mini 8.
Huh?
It's also known as Mini 8. It's like RG8 is big stuff. 58 is fairly small. 8X is a Mini 8. It's smaller than 8 and bigger than 58.
Oh, it's in between.
It's in between.
I didn't even know they had such a thing.
Yep, 8X. It's about the same size as RG59. But RG59 is
70.
RG59 is 75 ohm.
Yeah. So what's
Oh.
the same equivalent to RG8U then?
The 9913 or 213. 213 is very similar to RG8.
LMR 400 stuff?
LMR 400 is like an is like a 9913. Yeah, it's a really high quality 8
So that's the stuff to get then.
if you can afford it and if you have room to put it. It weighs a lot. So there are lots of ups and downs with all of these things. Okay, so now what we're going to do is go back to here and say that, okay, so what's the difference in coaxial cable as your frequency goes up? And if you look at that table again, what do we notice if we pick a single cable and we keep raising the frequency? What happens to the loss?
It goes up.
It keeps going up and it goes up pretty fast. So at 1 megahertz, you could get away with RG58. 0.4 of a dB per 100 feet. That's like nothing. You take the same cable and you run it at 400 megahertz and you lose 11 dB.
Oh my gosh.
So you're basically losing 92% of your power.
And that's why it's okay to use that RG58 stuff for CB radios.
Mm-hmm. But if you try to run anything else on it, the higher you go, the worse it gets. And that's why, for instance, a television station would want to run the biggest, fattest cable that they can, because they might operate at 800 megahertz, 600 megahertz, 700 megahertz. The losses are huge for small cable. Okay, let's see. So the electrical difference between RG58 and 213, right in the middle of that page. 213 is a bigger cable, so it has lower loss. The next one up is air insulated hardline. Hardline is even bigger coaxial cable. Typically starts at about a 1/2 inch and goes all the way up to 6 inches in diameter. Air insulated hardline is very, very difficult to use because you have to fill it with air that doesn't contain any what?
Moisture.
Moisture. Because what happens if you get moisture in your cable? It corrodes the cable, and then you have bad cable. So you have special considerations when you're using things that require air or nitrogen or something. Okay, source of loss in coaxial feed line, water intrusion. Every time you add a connector, it gets worse, high SWR. Moisture contamination, outer jacket, if it's not UV resistant, it causes the outer jacket to crack in sunlight, which lets it get wet inside, and that's bad. Okay, now we're into different connectors. All right, so I happen to have brought up a picture of a universal connector kit. I have one of these universal connector kits. So can everybody see that picture pretty well? Everyone see it okay?
I've made every one of them.
Have you? Okay. The one on the very left, those are PL 259s and SO 239s. Those are known as UHF connectors, but they are terrible for UHF. UHF actually stands for universal high frequency, and they should only be used at high frequency and maybe a little bit at VHF, but they're very, very common and they're easy to use.
The N connector is the best one.
The one on the right, those are N connectors. Those are good up to a few gigahertz in frequency. And notice that they also have gaskets inside them, which means that they are inherently watertight, or at least water resistant. Whereas PL 259s will basically just, leak like a sieve. So if you want to use, if you're going to be doing VHF and especially UHF, you're going to end up picking the N connectors, which are the ones on the right-hand side.
The PL 259 connectors have like different methods of making them anymore.
Oh yeah.
The old way of making them was where you basically had to twist the shield and pull them around through the hole and solder it to the outside, and then put the center conductor in the hole in the middle and solder it there.
I still do that.
And a lot of people just don't have the dexterity to do that.
I
Now
still
they
do
got
that.
the crimp ones.
The crimp ones are not bad. The crimp ones are not bad. What can cause erratic changes in its SWR? We haven't done SWR yet. SWR is standing wave ratio. So if you have connectors that cause an impedance bump, you can get an SWR bump in your. So that doesn't make a lot of sense to talk about without drawing this first. So we're going to have a 50 ohm cable. And then we're going to have a resistor, which is our antenna. And we're going to make this 100 ohms. So the analog to this is I'm going to have a string and I'm going to tie this to a doorknob. So if the door doesn't move and you take that string and you whip it up and down, you'll get a wave that travels down the cable. What happens when it gets to the doorknob?
Stops.
It does not stop. If it doesn't knock the doorknob off the door, what happens to the energy in the cable?
It shakes the doorknob.
Right? But if the doorknob can't shake, what happens to it?
It returns the wave.
It returns the wave. The energy goes like this. That is
So you're saying it rebounds.
It rebounds because the energy has to go somewhere. Energy can't be created or destroyed. This is this is basic physics. You have to do something with the energy. So either it knocks the doorknob off or it shakes the door. If it doesn't do that, the energy is going to, and you guys can try this. Take a jump rope and tie it to the door and watch what happens when you whip it. The energy comes back and it has to go somewhere. So you basically have energy that is traveling this way and energy that is traveling this way. If you just whip it one time, you'll see a wave that goes down and then back. That's a reflected wave. Now, the question is, what if you have a continuously generated series of waves that go down, making a continuously generated series of waves that come back?
They fill up.
They build up. Yeah, you'll actually see that the amplitude at any point in time, if they're adding together, could actually be higher than either of them if they happen to be arriving in the same place at the same time. That is why, if we look at the analog here with antennas and feed lines, we will see that we have standing energy, or energy that's going down through the cable, and some of it, because this isn't a perfect match, it's not a perfect mismatch either. Some of it gets dissipated and transferred into the load, and some of it bounces back as these red lines. Depending on what happens, they may be additive, they may be subtractive. Let's say that we have a transistor that normally runs at 22 volts to make that energy. The transistor has a maximum voltage of 30, maximum operating voltage of 30 volts. You have on this reflected energy 12 volts coming back.
Okay.
So how much voltage might you end up seeing in your transmitter if those happen to be
34.
unlucky enough to be in phase? 34 volts. And what did we just say can happen if the transmitter gets above 30 volts? Right, you fry your output transistor. So SWR, or standing wave ratio, is a measure of how well matched the load is to the transmitter or to the feed line that's feeding it. A perfect match would be a 50 ohm load, in which case what would happen is all the energy that you're sending out, it's like an infinitely long jump rope. It never comes back. You never see it again. That would be known as an SWR of a standing wave ratio of 1:1. And if you want to think of it this way, 50 divided by 50 is 1. If you had, let's say, 100 ohms, you would have a standing wave ratio of 2:1. Now, interestingly, it's not just one divided by the other one. Let's say I had 50 and 25. That would be a half, but you take the magnitude of the magnitude of the larger. So it's 50 divided by 25. That would also be 2:1. Now here's
It'd be the same.
It would be the same. It would still be a 2:1 mismatch. Because it's you
but
take
the
you take the bigger one divided by the smaller one. Now here's a big problem. Let's say you have a short circuit. What is the impedance of a short circuit? How many ohms? How many ohms?
0.
0. What's 50 divided by 0?
0.
It's not 0.
Oh, it's infinite. The other way.
Infinity.
Yeah. Sorry.
Okay.
Sorry.
So now let's do the other one. What's an open circuit? Open circuit's infinity ohms.
Mhm.
So then
What's
your
it-
ratio is real big.
Well, what's infinity divided by 50?
Infinity.
Infinity. So in other words, what happens is if you have an open circuit or a short circuit, like your antenna fell and is no longer connected, or you have a short circuit, the effect is the same. You get all your power reflected back to you. That would be an infinite SWR.
So if you unhook the cable from your antenna, and you'd be done.
Yep. So by convention, a mismatch of 2:1 is okay. 1:1 is perfect. 2:1 is okay-ish. 4:1 is a mismatch. Like you really don't want to be doing.
So if you have anything in between 2 and 4, it's
It's marginal. I mean, it's burning up a lot of power in your cable, because here's the other thing. What do we know about cable? What do we know about loss in cable? Where does power in cable go? If it doesn't go out the antenna, what happens to it?
goes dissipates in heat.
Dissipates as heat. Right. Okay. So now what we're going to have is a signal that transmits energy out. And we have a mismatch here. We don't know how bad it is, but we have a mismatch. So some of it goes out and some of it comes back. Well, let's say that we have a magic box we put right here, and this is called an antenna tuner. We saw one yesterday. It looks like this.
All right.
That is in this magic box. That makes your transmitter happy. That makes your transmitter think that there's a 50 ohm load connected to it. And the transmitter is now out of the picture. It doesn't care.
So that protects your transmitter,
Correct.
but not necessarily gives you output power
Well,
that you want.
Here we go. So that energy, the yellow line, gets back to the antenna tuner, and it has to go somewhere. That energy goes this way and goes back up to the antenna. When it makes it up to the antenna, it says, oh, I still have a mismatch. Some of the power goes out and some of it comes back down. While it gets the antenna tuner, gets reflected again, and some of it comes out and some of it goes back. So what do you see happening here? And some of it goes out.
Cable
many-
getting hotter and hotter.
Well, the power going out and back gets lower every time because each time a little bit of it goes out, right? But every time the power goes up and down the cable, what happens to some of the power?
Gets dissipated in heat.
That's right. So the worse the loss, the lossier the cable, the worse the situation becomes. So a high SWR exacerbates lossy cable. Now, the other thing is that because some of that power is going away, when you actually do your matching circuit, most matching circuits will be a part of an antenna tuner, and the antenna tuner will have an SWR meter, which measures power going out and power going back. So if a bunch of the power suddenly disappears coming back, it actually looks like your SWR is better than it really is. So lossy cable, like really lossy cable, can actually mask a high SWR because of the way that it's measured. Okay, let's see. Low SWR is a good thing. There's something called foldback, where transmitters will monitor the SWR that they see, and if they have too high of an SWR, they say, hey, I got to back this off. So if they ever get to a point where it says the sensor says that if I keep transmitting like this, I'm going to burn my radio up, it'll automatically shut it down. That's known as foldback.
Is that a hard, expensive item that comes in radios now?
No,
Or is it something that's
it's
very
all
easy?
it's all designed into it. Now, a lot of handheld radios will not have that. If I take a handheld radio and I disconnect this antenna and I transmit at high power, I will fry the output transistor.
Oh, okay.
I can almost guarantee that I will fry the output transistor. So don't do that. Instrument to use to determine SWR. It's a directional watt meter, power going out, power going back. If you want to look it up, there's a formula for calculating standing wave ratio from power forward and power backwards.
So, and it is a ratio.
Yep. So it's proportional to basically 50% is 50%, independent of how much power is being sent out. Okay, let's see. There's a device called an antenna analyzer, which allows you to basically run a test on an antenna, even on frequency bands where you don't have privileges. It's like a 1 milliwatt transmitter, which is an unlicensed thing, and it measures power out and power back. And you can sweep across a large number of frequencies, including those that aren't ham bands.
Does it check your cable too?
You can, yeah. I mean, if you put a 50 ohm load across the cable, some of them have insertion loss checkers. You know, they know how much power is going to go out. Sometimes you'd short the other end. It'll tell you how much power is coming back. You can figure out how bad your cable is.
Huh.
And actually, if anyone's really interested, look up something called a nano VNA. Does anybody have a nano VNA? It's basically a Chinese made network, vector network analyzer. And for $100, it basically comes very close to what a $10,000 piece of test equipment can do, as far as testing cables and testing antennas and impedance and things like that. The primary purpose of a dummy load is a fake 50 ohm resistive antenna. So essentially simulating a perfect antenna. And in particular, it's a non-inductive 50 ohm resistor. So
Oh, you
question
can
is,
buy them things on Amazon.
yeah, you can. So, okay. So let's say I have a 50 ohm resistor. I use this as my fake antenna. Why would I require this to be a non-inductive antenna, non-inductive resistor? Think hard, everybody. In other words, this
So
is
that you don't change the characteristics of your cable.
well, we're going to go back to impedance, resistance, and reactance. Resistance is going to be 50 ohms. You remember what reactance is for an inductor? Notice we have that letter F in there, which is frequency. At low frequency, my reactance portion is going to be here. At high frequency, my reactance portion is going to be here. So what's going to happen to my impedance as frequency goes up?
Gonna get higher.
Going to get bigger and bigger. And is my 50 ohms at 50 ohms anymore? All of a sudden, my 50 ohms becomes 100 ohms. But at a different frequency, it's 90. At a different frequency, it's 70. That's not a very good test device, is it?
And so you're using a 50 ohm
Carbon resistor, or they call it non-inductive wire wound also. Basically, it looks like this. It has wire, but it never completes a loop. And if it doesn't complete a loop, yeah. If it doesn't complete a loop, it doesn't make a loop. It doesn't have it's basically not an inductor. It has a little inductance, but not much.
So you're better off doing the carbon one.
But then you have power handling capabilities that you have to make sure it meets. So if you're going to run, let's say you have 1,000-watt a 1,000-watt dummy load, it has to be able to dissipate 1,000 watts of heat. So if you can find a carbon resistor, it might be this big.
That thing's gonna be huge.
It would be huge, yeah. Or you could use a whole bunch of them in parallel, and then put them inside a big heat sink with a fan.
Yeah, but then you still end up with an inductive load if you do all that. You got all them connectors.
No, it'll be fine. You can build it. All right, modulation and bandwidth. Okay, so we're gonna have to do a little bit of pushing here with the modulation. So if you've got some really good questions, throw them out, but I'm gonna show some pretty detailed stuff here. Okay, here we go. We're gonna look at an SDR. So can everybody see that okay?
Looks good.
Okay. All right, so we're now looking at an SWR and a software-defined radio. So what we're looking at is a single sideband signal. It goes from 14,208 to 14,210. It has a bandwidth of about 3 kilohertz. So that's 3,000 hertz. If we take a look at a different signal, for instance, let's go to a different one. So we're now looking at Morse code. You will see that it has a bandwidth of something in the order of, I don't know, 50 to 100 hertz. So this is physical space that a signal actually takes up on the band. Every signal, if it contains information, takes up space. The more information that's sent, the more space it takes up. So for instance, if we look at a digital signal, so that's a digital signal, another digital signal. The more information that something takes, the more space it fills. So these are fairly narrow. This is a mode called PSK31. That's 31 baud. It fills up 31 hertz of space on the band. It's a very, very narrow bandwidth.
So if you have a bunch of those, you can transmit a lot of information at the same time.
Yes. And in fact, what that means is we've got, okay, so we're going to have our band, and it's limited in space, and we're going to have our Morse code signal. This takes up about 150 hertz. Our single sideband signal is going to take up about 3000 hertz. Our AM signal is going to take up about 6000 hertz. And then we have our digital PSK31, which is going to take up about 31 hertz. So the benefit of doing this is that the narrower the signal that you can transmit, the more of them you can put adjacent to each other without interfering with each other. The other benefit is that because we covered filtering a little bit, you can actually build a filter which can allow certain information to go through and block others. So by selecting, I'll pick a different color. By selecting different components, different combinations and values of capacitors and inductors, what you end up with is, depending on how you arrange them, you can build a filter that allows everything below a certain frequency to go through. You can build another one that allows everything above a certain frequency to go through. This is called a low pass. This one is called a high pass. If you take two of them together, you put a low pass and you daisy chain it with a high pass, you get a band pass. So the benefit of doing this is that, okay, well, you can take your low pass and high pass and shift them so that you get a very, very narrow band pass. That might look like this, in which case you're able to use those two different filter components and generate something that allows you to tune just one signal in. So, and because the bandwidth is a limited resource, I mean, there's only a certain amount of space. The whole frequency band, let's say the 20 meter band is 14.000 to 14.0, or sorry, 350. That's 350 kilohertz. Of bandwidth. That is physically allotted space. This is why we can't take a signal with a bandwidth of, let's say we want to do FM. FM takes up between 10 and 15 kilohertz. That would be about 5% of the entire band for one signal. We can actually do high-speed television. High-speed TV, which is ATV or NTSC television, is 6 megahertz. The whole band here is only 350 kilohertz wide. So we couldn't possibly do that. And that is why the really high bandwidth stuff is relegated to really high frequencies, like the UHF band, where there's a lot of room. We don't have very much room here, so we tend to prefer the really low bandwidth stuff. Now, unfortunately, that also means that low bandwidth takes up, it can carry very little information, which means that, voice is, compared to what we're using right now, which is, gigabit Ethernet or 200 megabits of bandwidth, we can convert our voice and transmit it over it very, very easily. We can also, do 1,000 other voices at the same time and transmit it on that same channel. Right? We couldn't do that on the high frequency band. FM and phase modulation, FM and PM are typically used for voice repeaters. So if we do our FM, instead of looking at the high frequency band, we're going to look at the VHF bands, and we're going to pick 2 meters, which is 144 to 148 megahertz in the United States. So this is a 15 kilohertz FM or PM, which is phase modulation. FM is frequency modulation. PM is phase modulation. There's plenty of room to put that. And we can also pick another one, and maybe another one, and another one, and another one, and another one, and another one. We can put a whole bunch of FM signals there. But that 15 kilohertz again would take up so much space on a much smaller band like you'd find on HF that we don't allow it. Okay, so when we talk about frequency modulation versus amplitude modulation means we're changing the amplitude of a signal over time. So that could look like this. And so that is our envelope. That is basically a mapping of your voice. When we modulate something, we take a frequency which is way higher, much higher. So this might be 3,000 hertz is our voice maximum, and this could be like 10 megahertz. We will basically do this and shape our signal so that it basically contains the envelope picture, and then we get rid of the envelope. This is amplitude modulation. When we do amplitude modulation and we have a frequency spectrum, here's the center frequency. So there's that 10 megahertz. This would be 10 megahertz. And we create side bands that fill up space. So this is the plus side and this is the minus side. This would be known as the upper sideband, and this would be known as the lower sideband. Most of the time we use upper sideband, and through some creative electronics and mathematics, one thing we can do is when we go to transmit these signals, we can say, well, the upper and lower sidebands are mirror images. I guess we could do away with that side. And well, we don't really need that carrier signal. That's just a marker. So we'll get rid of that too. So instead of transmitting with a bandwidth of 6 kilohertz, we've basically transmitted only about 3 kilohertz, and we still have the same full amount of information that we need to get across. The one thing we have to do is when it gets to the other side, we actually have to put in a reference frequency so we can actually listen to the sound, which is exactly what we were doing when we switched over to listening to voice using that software-defined radio in the Netherlands. So most of the time on most ham bands, with the exception of 40 meters and longer wavelengths, we use upper sideband by convention. Now, most people think of FM as something that is, commercial band radio, and FM on the radio that you listen to for music is 88 to 108 megahertz. That actually has a bandwidth of about 200 kilohertz per signal, which is why we can't use FM radio to send signals on the AM band, which is at the 1 megahertz bandwidth. You'd be able to send like 5 signals. It'd be 5 FM channels, but that's not really practical. This is a wideband FM. It's a really wideband FM. And when I say FM, instead of modulating the amplitude of a signal, what we take is a carrier wave. that looks like this. And depending on the speech that is going into it, what we will do is at certain times, we will increase the frequency slightly and then maybe lower the frequency and increase it and lower it. And what that does is it makes it contain the information of the voice that's going in, which is known as the modulating signal. So because we're modulating the frequency, not the amplitude, we are simply just changing how fast it's going. So if it's at, let's say, 146 megahertz, for this little period, we might be at 146.1, and right here we're at 145.9. So that would be like plus or minus a little bit. Actually, let's go 146.05 and 0.95. That would basically mean that if we looked at our frequency spectrum, we would be filling up a certain amount of space with our signal with that center frequency picked. That is basically how FM works. We can use it for voice. We can use it for something called packet radio, which is digital. However, FM has a really nasty habit. If you're using FM and here's a signal coming into your system, and here's another signal coming into your system, which is of a lower amplitude, this one wins. The lower one essentially completely disappears. And if they happen to be at about the same amplitude, then you're really in trouble
Sound funny.
because nobody wins. They both disappear. And when I say disappear, they just basically completely interfere with each other and it's totally unintelligible. And this is known as a double. If you're on a repeater and you hear somebody say double, that basically means that nobody won and we couldn't hear anybody. We couldn't hear either person talking. If you're talking on VHF, on 2 meter band, most people will be using FM. However, when it comes to doing some of those more esoteric modes, such as tropo or e-skip, any of those, you typically will use a horizontally polarized antenna, and you're typically going to use SSB. You could also use CW. You could also use digital. Basically, these are known as weak signal modes because FM, because of how it's built, FM does not carry over longer distances quite so well. These you can dig out of the noise quite nicely. Okay, let's see. Let's see. CW is continuous wave. That's known as Morse code. Basically, I take a signal and I do this. That's what it looks like. Doot, doot, doot. That's a letter O.
They used to use Sparks for that.
Yeah, we don't use that anymore. Spark is very inefficient. Let's see. To send this, you could use a straight key. You could also use an electronic keyer, which has 2 paddles on it. One side does dits and the other side does DAWs. The nice thing about it is that it's automated and it allows you to go a lot faster than you would normally be able to go. Okay, so now we're getting into the digital modes. And digital, all right, there's something called packet. Packet is basically packets of information being sent digitally, so ones and zeros. Packet radio has something called ARQ, which is automatic repeat request. What ARQ allows us to do is if a packet gets lost because there was noise, the receiving station can say, I didn't get it, please send it again. And it'll do so automatically. We can also combine packet radio with mapping over the internet or using some other GIS software, as well as a GPS receiver to send information about position, altitude, direction, velocity, and put it on a map. So this is used for lots of different things, tracking vehicles, tracking balloons as they travel, tracking rockets, and that's known as APRS. PSK is phase shift keying, where instead of modulating the frequency or modulating the amplitude, we change the phase of a signal as it's being transmitted. Typically, we'll do a 180-degree phase shift. So if we have a sine wave that's going up and down, and all of a sudden there's a 180-degree phase shift on it, and it's basically it has a discontinuity, that means that there was data sent, right? Usually like a 1 or a 0, depending on what it is. And that allows us to modulate a signal and have a very, very narrow bandwidth. DMR is a method by which it's called digital mobile radio. There are a couple of different versions of it. There's DMR itself. There's something called Fusion, and there's another one called D-Star. It's basically just a different protocol that essentially allows you to have a single repeater channel and split it in half time-wise, so that all the A stations get to use it for half the time, and all the B stations get to use it for half the time. And it's digital, everybody's time synchronized, and everybody's voice is converted into ones and zeros. And essentially it just says, okay, A stations, it's yours. B stations, it's yours. So your radios are all synced up with the repeater. So it seems like there are two different channels on one channel, and neither group knows of the existence of the other one. So it allows more people to use the resource that we have.
And and it's hooked up to the internet?
No, it can be, but not necessarily.
What it says in books, I'm just.
It can be.
Oh,
Which of the following activities is supported by digital mode software and WSJTX? Okay, so Joe Taylor, who's a Nobel laureate, Nobel Prize winning physicist, he was really big into EME, Earth, Moon, Earth, or moon bounce. And so he created, along with some graduate students, a new mode of operation called JT65, which has become FT8. And it is exceptionally good because it's a very, very low data rate, and it's also very robust as far as its error detection and correction. We use that for meteor scatter, really high speed, weak signal propagation, and moon bounce. We also use it for a lot of terrestrial communications. Notice this FT8, digital mode for low signal to noise operation. A mesh network. Mesh network is basically taking Wi-Fi equipment and repurposing it to create a network that is self-healing and deterministic, where you basically will send information and it will figure out, the network itself will figure out how to get it from point to point. All right, let's see, safety. Current flowing through the body, it takes about 10 milliamps to really, really, really hurt you. Any more than that can kill you. 10 milliamps is not a lot of current. Let's see.
Pacemaker.
Well, yes. Well, a pacemaker is very low current. Let's see. The black wire in a 3-wire system in the United States, black is the hot wire, the white is the neutral, and the green is the ground. A good way to guard against electrical shock, you want to ground all your equipment, and you want to install fusing, and you want to have mechanical interlocks in high voltage circuitry. I had a shortwave radio when I was a kid. I opened up the lid, I stuck my finger in, and I got a 250 volt DC shock, which left me with memories of getting a nice high voltage shock. The purpose of a fuse is to remove power in case of overload. Why should you install a circuit breaker or a fuse? You put it in the in series with the hot wire. The hot wire, again, is the black wire, so that if something overloads, it'll break that circuit and cut off the high voltage. You only ever want to use a replacement fuse that's the same value of the one that came out, because you don't want to allow more current to flow than was designed. You could start a fire, as we talked about yesterday. Power supply, when you turn it off, power supplies have big capacitors in them. When you open up a power supply, the capacitor could still be charged up. For those people who have memories of old television sets, a TV tube could store about 25,000 volts on it. And when you opened up an old TV, you would typically want to discharge that TV tube because essentially it acted like a capacitor that was storing 25,000 volts. And if you didn't do that on purpose, it could happen accidentally, and then you get a really nice zap.
I had a friend of mine, and he was taking the electronics class when I went to high school, and he pulled a TV tube out of TV. It was like one of those great big color ones. And he pulled it out, and this was a rather large kid, and he put the connector of the backside of the tube up against his belly, and
Oops.
and wow, yeah, because like he dropped it.
Yeah.
And of course it made a mess everywhere.
Yeah. I grounded on a key grinding machine. I got probably 220 through me. All I saw was blue white light and threw me back about 6 feet.
Yeah. Say
I'm
electrical.
surprised I'm still alive on that one.
Yeah. Well, I was 10 years old when I shocked myself like that, and I'm like, oh, I'm still alive. Good. 12-volt storage battery, a charged or overcharged or undercharged battery generates hydrogen, which is why if you have a spark around it, it can cause the battery to blow up, showering you with sulfuric acid. So be careful. Okay, we are on to antenna and tower safety. I don't have a tower, but everybody puts up antennas. The most important thing to remember is expect to find power lines where you don't expect to find power lines. Anything you're using needs to be at least 10 feet away from power lines if it falls and when it's standing. Electricity can jump very easily. And there are, even this past year, there are reports of, people that were doing an antenna work party and he kind of forgot what he was doing. And the antenna that he ran over to grab because it was going to get tangled up in something, contacted a 7,200 volt line, and he died. This was a really experienced antenna guy. So it can happen even when you're not thinking about it. If you don't ever use a utility pole unless you own the pole and it doesn't have any services on it. Utility poles are great because they're strong, but they also have, in some cases, like we said yesterday, 13,200 volts on those wires. So don't climb them. Don't put anything on them. During a transmission, you can get an RF burn because that current flows on the outside. You also get a significant voltage on the outside of an antenna. If you touch an antenna wire when it's transmitting, you can get zapped, and it really hurts. It makes a little puncture wound. It's called an RF burn. When climbing a tower, wear a helmet, wear a harness, and make sure that you're safe in doing so, and never, ever climb alone. Because if you get stung by a wasp or something and you let go, you might just end up hanging there for a while if you're wearing a harness. And then you can die from just hanging there if you don't have help. So never climb by yourself. When using a crank up tower, don't ever climb it if it's extended. Or if it is extended, make sure it has locking devices in place. A turnbuckle, we sometimes use guy ropes and guy wires. A turnbuckle is designed to tension guy ropes. They tend to vibrate in the wind, and they tend to loosen in the wind. So we use a wire that goes through the turnbuckle to hold it in place. We follow all electrical codes. If we're going to use ground rods, we use 8-foot ground rods. You want to ground your station, you pound an 8-foot ground rod into the ground. Don't use the water pipe unless you absolutely have to. Do not ever use a gas pipe, that is typically a very bad idea. If you're going to be grounding a tower and it has 3 legs, each leg gets its own ground rod, and you ground them all to the tower and then to each other. You want to give lightning a really easy path to ground. So when you're doing that, you never use long wires, and you never make any sharp bends in your grounding wires, because lightning, instead of going around a 90-degree angle, will just jump to somewhere else, which is kind of like defeats the purpose. If you're taking all your ground rods, you want to bond them together with a conductive strap or a really, really heavy wire. Don't solder it, because lightning generates a lot of heat, and lightning will melt solder, and then you don't have an electrical connection anymore. So welding or mechanical bonding. A lightning arrestor and a coaxial feed line. It goes near where the wires enter the building. It's designed to basically, if you are unlucky enough to have lightning strike your antenna, the high voltage will travel down the center conductor of the cable. Between the center conductor and the outside, you typically will put a gas filled tube, which will ionize from the high voltage, which will cause a conductive path, and hopefully shunt your energy to the ground through your ground rod before it makes it inside to destroy your equipment. Now, it might also still cause some equipment damage. So if you know there's a lightning storm coming, it's a better idea to switch all your equipment off and disconnect all the antennas. That'll protect it. RF hazards and radiation exposure. We think of radiation as radiation, X-rays. But any kind of electromagnetic energy is radiation. Radio waves are a very low energy radiation. Unlike UV, the reason that ultraviolet causes sunburn, the reason that X-rays can cause cancer and gamma rays can cause cancer, is because they have enough energy to get into your cells and actually break things apart. Radio waves, they can cause, like in a microwave oven, they can cause heating, but they won't kill you. At least on a genetic level. They don't damage your DNA. We follow this thing called FCC OET Bulletin 65. That is the standard for RF emissions safety in the United States. So we have emission safety, we have exposure safety. It can actually be quite complicated to figure out what an antenna is doing. It's a lot easier, however, to go to a website, for instance, that somebody has come up with a calculator for doing this. You punch in your power level, the frequency you're on, and what your antenna looks like, and it tells you whether or not what your safe distance is. There's also, when you're looking at safe distances, there are people who know what's going on and people who don't know what's going on. When we put the station in at the Eugene Science Center, people who know what's going on are the people who are sitting at the equipment. People who don't know what's going on, that would be called an uncontrolled environment. That would be all the other people in the museum, which is basically everybody. So essentially, we had to take a look at where the antennas were, how much power we were running and on what frequencies, and do calculations to make sure that those exposure levels were safe for everyone who would just be visiting the museum. So, and as a licensee, you are required to do this anytime you put in a station. That might mean that if you put a ground mounted antenna, actually mounted on the ground where somebody could walk up to it, you put up a fence around it. If it's on your property, you have an external fence, that's fine. If it's let's say you're doing it on a temporary basis in a public park, you want to put up some kind of protection, at least indicating that, RF fields might be present, do not touch. The definition of duty cycle is the percentage of time that something is happening. If you're transmitting with a 50% duty cycle, that means you're 50% on and 50% off. If an exposure limit is based on 100% duty cycle, if you cut your time in half, you can raise your power by a factor of 2. If you cut your power by a factor of 4, you can raise your power. If you cut the time by a factor of 4, you can raise the power by a factor of 4 so that the duty cycle and the power level work together. Exposure limits vary with frequency because the human body absorbs energy at certain frequencies better than others. The peak is at 50 megahertz, which is 6 meters. A half wave is about 10 feet long. It turns out that we absorb energy better at 50 megahertz than any other ham band. Let's see what affects the RF exposure of people near an amateur station antenna. Well, you have the antenna radiation pattern, as we were talking about yesterday. If you have a dish and you point it right at somebody, they're going to experience a lot more discomfort than somebody who is standing behind or to the side. So the pattern of the antenna, the frequency, the power level, and how far away somebody is. If you point that dish antenna at somebody 100 miles away, there's probably going to be no impact. But if they're 20 feet away, you're probably going to notice something. What can reduce exposure to radiation, RF radiation? Relocating antennas. That's a great thing to do. You raise them up higher. How can you make sure your station stays in compliance with safety regulations? If you change a transmitter, that's significantly different. You know, you go from 50 watts to 100 watts, then you do another survey. Okay, station setup and operating controls. Okay, so this is Ohm's law. Why would you use short heavy gauge wires? Because the bigger the wire is, the lower the loss in power. The shorter the wire is, the lower the resistive loss. So if you're hooking up a transmitter to your car battery, you want big fat wires, and you want those wires to be as short as possible. So now we're going to talk a little bit about efficiency. So we have a 12-watt power supply, a 12-watt radio, and it's a 50-watt radio. So to make 50 watts, we typically would need about 100 watts of input power. Efficiency is power out divided by power in. Most of the time for RF transmitting equipment, it's about 50%.
Oh, that's wasteful.
So, well, it heats up. You also have electronics. So in order to generate 50 watts of RF, you would need about 100 watts of DC power. So in order to generate 100 watts of DC power at 12 volts, P equals I times E. I equals P divided by E is 100 divided by 12 is about 8.5 amps. So you typically go with something a little bit bigger, which is why they say 13.8 volts, which is your nominal DC power they're at 12 amps. That gives you a little bit of headroom. The same reason that if you're running a 100-watt transmitter, you would need about 200 watts in at 12 volts. That would translate to about 16.5 amps. So typically we go with a 20 plus amp power supply. And you look at that and say 20 amps, well, 20 amps times 12 is 240 watts. Huh, I'm using a 240 watt power supply to make 100 watts. And that's because of the fairly low efficiency of making RF power. Okay, for digital mode operation, in order to key a radio, you have 3 lines. You have push to talk, which is your microphone button. You have your audio in and your audio out. Audio in is from your microphone. Audio out is to your speaker. If you have a computer, you have the computer driving some kind of relay that controls the push to talk line. And then the input to the radio, this is your speaker from your computer. And the output from your radio goes to the microphone input on your computer. Just 3 wires that'll allow you to get it done. Okay, which of the following could you use to cure distorted audio caused by RF current on the shield of a microphone cable? Well, okay, it doesn't matter if it's RF cable or microphone cable. Again, you have current flowing on the shield. We would do this. And that is a ferrite. And again, the job of a ferrite is to take current that's flowing on the outside, which is generating a magnetic field, and dissipate it inside that material, thus choking it out, choking the energy. Which of the following conductors is preferred for bonding at RF? Now, this is an interesting question because it comes down to how does radio frequency energy at AC flow? Well, it flows on the outside of a conductor. So if you have a conductor that's circular, cylindrical, versus one that's the same amount of material but squashed flat, you get more surface area with the one that's squashed flat. So you have lower resistance to RF energy flow using a copper strap than you do with wire, which is why we would typically do that. So the next question, where should the negative power return of a transceiver be connected in a car? Well, you typically will take your power line, your power lead, and go right to the fusible link or right to the battery with its own fuse. And some people, if you think about how cars are built, all the lights in a car, they only have a wire going out to turn it on, and they receive their ground, right, their negative terminal, from the frame of the car. The frame of the car is assumed to be okay, especially for small light bulbs, but it is not an RF ground. It's not a high current ground. So in order to get those electrons flowing from the battery to the radio and back, we take big wires and we go straight back to the battery. How do you determine the length of time that equipment can be powered from a battery? A battery has a capacity, right? It has a certain number of electrons that it can provide, period. Defined by its size, defined by its chemistry. It can make a certain number of electrons at a certain voltage. That's just how big it is. So if you figure out how many electrons you take from the battery per unit time, that's a current. Okay. So if I know how much current I can draw, and I can look at the battery capacity and say how many electrons are there available, I know how much time I can use the battery. So it's current times time. That's measured. That's
I have an
measured.
observation.
Yeah.
You know, when you have a lead acid battery, they tell you how much capacity is in those things, even if you get a deep cycle battery.
Mm-hmm.
But you can only count on actually having 50% of whatever it says, because you can only drain any kind of lead acid battery halfway before it starts to degrade itself.
It depends on the battery chemistry. Like
Right.
some batteries, I mean, typically a battery is going to be measured in amp hours. And it's also true that, let's say you have a battery that's 100 amp hours, you can pull 20 amps for 5 hours or 5 amps for 20 hours. But the higher your current drain, what's going to end up happening is if you pull it faster, you're going to generate more heat, which is going to basically reduce the overall capacity that you're getting. So yes, that is true. Certain battery types are better for high dissipation, for high current dissipation than others. So lead acid, they're okay. I mean, I've got a deep cycle battery that I use. I've also got a lithium iron phosphate that works really well, especially at, pulling like 1/10 of the capacity for 10 hours. And okay, so we are on to operating controls. Everybody, how about a 5-minute break? Does
Okay.
that work? Good?
Yes, please.
Okay, 5-minute break. Anybody with comments or questions or anything? All I can say is it must be early.
Very early. So this is more of a technician class, or is it a general knowledge?
Well, I mean, it's specifically for it's specifically for getting ready for the technician license, but I cover more than that. So,
Yeah, that's what I thought. I felt like I'm learning more than I did in my tech one.
well, that's the goal.
Yeah.
Well, did you look at the first, did you look at the video from yesterday?
No, I didn't. I was out all day yesterday, so
Okay.
I missed that one class.
Yesterday we covered a lot of RF stuff. So depending on, I mean, as I was saying yesterday, the stuff that I'm going through, I mean, this is a radio class. I think of this as a radio class with a focus on the technician, but if you're comfortable with this material and you look at, the specifics that are specific to the general class license, you can pass that pretty easily.
Yeah, I don't know what my score was on the test, but the technician was fairly easy, just as long as you repeatedly cut research and go over the material, so you just memorize the questions, really. But
Yeah,
it's
well,
good to,
yeah. I mean, but I'm teaching the stuff behind it.
yeah, and I
So,
appreciate that, because there's a lot of stuff behind it that we don't realize, especially for safety.
yeah, and there's a lot of applications to the general exam too.
Sure.
I mean, the RF doesn't change depending on the license class. RF is the same.
No,
Basic electrical theory is the same, independent of license class. The only thing that changes is the specific rules and regs based on, bandwidths and the frequency bands you're allowed to use, the modes you're allowed to use, the power levels you're allowed to use. Basically rules and regs specific to that license class. But RF is RF. Antennas are antennas.
Yeah.
I teach, there's some stuff that's a little bit more in depth. Like when you get to the extra, you have Smith charts. Smith charts are an application of antenna matching or impedance matching. And to be able to understand what, instead of saying, that the loss goes up for a given cable, the question will be how much loss do you have? And you actually have to calculate it instead of just knowing that it does get worse.
Well, that's what I've realized, is that my antenna and cable it's too far away and the cable's too long.
Mhm.
And I figure I'm losing a lot of strength.
Depending on the band. Yeah.
Yeah, 2 meters generally.
That's why for most stations that put up a repeater, they use hardline. If it's, unless the transmitter is actually way up on the top of the tower, which it usually isn't. If there's a little building down below and there's, 150-foot run up to the top of the tower, you better be using hardline.
What if I just put an amplifier in along between my radio and the antenna?
Well, I mean, an RF amplifier or a preamp.
Either.
If you have a weatherproof RF amplifier and you have deliver power to it, sure.
Okay.
I mean, that's how cable TV works. So
Scott, where do you get these videos that you're doing?
I sent out a link last night.
To email?
Yeah.
Oh,
Okay, I didn't see that. But thank you.
Uh-huh. Okay, here we go. Operating controls. Okay, so this is a very practical part of the class. This is where you finally start to learn how it is that we, use a radio. All right, microphone gain. Mic gain is basically, we can do this. And if I have somebody that's talking quietly, if I have a mic gain control, that can basically crank up the little audio amplifier. So if you're talking too loudly, and I don't know if I'm doing that now, basically you get distortion. It essentially overdrives the amplifier. and creates distortion. What you'll see here is that most things that we're talking about cause distortion. These are just things that cause distortion. Overdriving a microphone. If you're tuned off frequency, for instance, that'll cause distortion on FM. If you're tuned off frequency using single sideband, or if you're tuned on the opposite sideband, it'll be completely unintelligible. How do you change a transceiver's operating frequency? Well, if we have an HF transceiver, it's typically got a tuning knob. If I've got a 2-meter transceiver, there's my keypad. It also has a tuning knob up top. I just punch in a frequency, or I can call up a memory channel, or I can spin the tuning knob. What's nice about most transceivers is that they do have memories. That handheld transceiver that I have, I believe, has 1,000 memories, which I've used about 150. It's really hard to use 1,000 memories. Apparently you can do it, but I've never been able to. The scanning function of an FM transceiver, this radio, again, it has 1,000 memories in it. All I have to do is scan. It allows me to basically do a scanning function and spend a little bit of time on each of 100 different frequencies so I can look for activity. The squelch function. Okay, so what we're going to do for squelch, I think I still have WebSDR open, I hope. Okay, here we go. I'm going to share my WebSDR. Hopefully. Okay. Essentially, when there's no signal, that's what squelch does. If there's nothing above a certain level, squelch just mutes the receiver. Squelch is a wonderful thing, especially if you're listening to FM. How do you listen for weak signals? You turn off the squelch. Okay, repeater offset. Okay, so now we're going to talk about how a repeater is built. Okay, as a technician class licensee, you are permitted to build a repeater. Now, it doesn't mean you can get a frequency for that repeater. You're going to have to apply for one, but you're allowed to build one. So here's your receiver, here's your transmitter, and here's your controller that runs in the middle that controls both the receiver and the transmitter. You also have a duplexer. Okay, so if I were to just take my transmitter, let's run this up to an antenna. And you know what? Let's get rid of the duplexer. Let's get rid of the duplexer. We're just going to put an antenna up over here and another one over here on the receiver and the transmitter. And they're separate antennas and they run through a controller. Okay, so the published frequency of a repeater is, let's say, 145.45 megahertz. This repeater is also published to have an offset of negative 600 kilohertz, which means that it will be receiving at a frequency 600 kilohertz lower than its transmitting frequency. So the receiver will be listening to 144.85 megahertz.
I always wondered how that worked.
Yep. Okay, so now your signal is now transmitted on 145.45 and your receiver is receiving 600 kilohertz below on the 2-meter band. Depending on where you are, it could also be plus 600 kilohertz. On the 70 centimeter band, it could be plus 5 megahertz or negative 5 megahertz. But for now, what we're going to do is just go with negative 600 kilohertz for the offset.
But what you say, it's published, so it's commonly known.
Yes, this is how to use the repeater. People
Right.
want to, the owner wants people to use the repeater. This is what they tell them. Okay, so the other thing to do is there is on the receiver, there is a filter that is looking for a subaudible tone called CTCSS usually. This could also be looking for a digital coded sequence of which is something called DCS. This is a tone, and this is a sequence. It could use both, or either, or neither. More than most repeaters use a CTCSS, and this is anywhere between 67 and 250 hertz. So those are tones that are very, very low in pitch that most people can't hear. The receiver is looking for that specific tone. This is also known as a PL when Motorola invented it. It's also known as private line. So what it's basically saying is, I hear this information, I hear this transmitter coming in on 144.85, but I'm looking for a tone of 100 hertz, and I don't hear that tone. That basically causes the receiver to not accept the signal.
Ah,
So if the receiver is set for a tone of 100 hertz, and you are transmitting into the receiver with a tone of 100 hertz, then the receiver will accept your transmitted signal. At that point, the receiver then, the RX, sends a note to the controller that says, okay, we have a signal coming in. The controller says, okay, am I busy? The answer is no. It sends it along to the transmitter, and it retransmits it on a different frequency. The controller is also responsible because this is an amateur radio station, is it not? The whole thing is a station. The controller is responsible for IDing the signal, independently of the signal that's coming in from the receiving station or from the transmitting station. The repeater has to ID itself. So independent of what's coming in, like the repeater that I'm the trustee of, it has to identify every 10 minutes as W7PXL. That identifies this transmitter to make it legal.
how does it do that?
Morse code. It's a Morse code IDer that it superimposes on top of the audio.
Oh, interesting.
What is okay? So that's repeater offset. Okay, a digital mode hotspot. All right. A digital mode hotspot. Okay, so now we're getting into VoIP, which is voice over internet protocol. So here's VoIP. That's voice over internet protocol. This could be a telephone. The phone connects to the internet. If anyone has an internet-based phone, whether you have a landline or not, you have an internet-based phone. At some point in time, your audio is being transmuted into digital so that it can be sent as ones and zeros along through the internet, and it comes out somewhere and gets transmitted back into audio. It gets converted back into audio somewhere. The internet does the switching of all the ones and zeros. This is known as voice over internet protocol. We do this over the radio also. There's no reason that has to be a phone. This could be a handheld radio with a hotspot, which is a receiver, an RF receiver that is then connected to, let's say, a 5G network. The 5G network goes to the internet, and then this comes out through the internet to another hotspot to another radio somewhere, so that two people can actually be on their radios using voice over internet protocol to connect them over longer distances. Now, interestingly, this internet does not have to be there. This could actually be something called mesh. We can actually take our voice over internet protocol and we can connect over long distances using high-speed radio links, in which case it becomes kind of like a parallel internet.
That's the same thing like what you do when you set up a mesh network in your home.
Yep. Exactly. Okay, a talk group on a digital repeater. A digital repeater, it again is like DMR, digital mobile radio. It has like a channel A and a channel B, or a channel or a red channel and a blue channel. Those are color codes. And those codes allow you to basically talk with the time synchronized group A or group B. Now, if you happen to have a networked repeater where the repeater is connected to the internet and is connected to another repeater somewhere else, if they're all time synchronized, all of those people who are synced up as group A can talk to each other in real time, independently of group B, who is using the other half of the time. So this is kind of like an internet-based talk group. It's one of the cool things that digital mobile radio can do.
Party line?
Yeah, oh, it's a repeater. It's just a repeater over the internet. Every repeater is essentially a party line because you're not allowed to encrypt anything. DMR, a digital mobile radio code plug, and it contains all the access information for repeaters and call signs. Part of DMR is sending data along with your voice transmission because it's all digital anyway. So that allows the code plug basically has all the information that you would need in your radio to connect radios together. A digital voice transceiver, you enter the group's identification code. The color code must match the repeater color code for group access. So you have color code red. If you want to participate in a particular group, you would set it to red. Now, I'll be honest, I have not spent a lot of time on DMR repeaters at all. I do mostly analog, but this gets really useful in areas where there's a really, really high usage of repeaters because it allows people to basically double the number of people using repeaters. It splits the time in half. D-Star. D-Star is another form of digital voice over the radio. And D-Star has, one of the benefits of D-Star is that it sends a fair amount of information along with that voice that you're sending. One of the things it sends across is your call sign. So you have to program your call sign into the radio. I hope my wife gets that. Hold on a second. Okay. All right. Let's see. Next thing. Let's see. We're talking about.
Daystar?
D-Star. Well, we talked about D-Star. Okay. Okay. So selecting filters inside a radio. There are many reasons to select filters inside a radio. And one thing we're going to do is we're going to select this. Can everybody see that? We're good? Okay, so now what we're going to do is we're going to select CW, which is Morse code. Well, okay, let's pick one. Now, notice we could take this and we could make our filter really, really wide. And what do we hear if we do that? We hear noise and we potentially hear multiple different signals at once. But the question is, why would we want to? By selecting a nice, comfortable filter bandwidth, we can select one that's appropriate for what we're doing. Now, if I switch to sideband and I go up here to the voice band, there's one. Okay, so notice I can make this super wide. There's no reason to make this any wider than it needs to be, right? What happens if I make it really narrow? A lot of the information is getting lost. So it's very important to select a bandwidth that's appropriate to what you're listening to. For Morse code, a good filter bandwidth is 500 hertz. For voice, a good bandwidth is about 2400 hertz to 3000 hertz. If you want to control what your receiver sounds like, you want to change the frequency, there's something called an RIT, which is receiver incremental tuning. Another name for this is a clarifier. It allows you to separate the receive and transmit frequencies so that you can listen to, when you're listening to another station, if they're a little off frequency, it allows you to tune them in without drifting off frequency. PTT is push to talk. If anyone has seen a handheld radio, push to talk. That's your push to talk button. What it does internally is that it grounds a transistor. The transistor will switch the receiver over to transmit. It'll switch the system over from receive to transmit when you push the button. All right, we are now into station equipment, receivers, transmitters, transceivers, and all other kinds of good stuff. Okay. Station equipment. Okay, a transceiver is a combination of the words transmitter and receiver. It allows you to receive and transmit. A transverter is a transmitter receiver converter. What it does is it actually uses something called a mixer and takes input from one frequency and transmutes it over to another frequency. It literally takes it. Let's say you have a 222 megahertz transverter. You might use 2 meters to transmit, and it will come out when you transmit on the 222 megahertz band. The function of the SSB CW FM switch on a power amplifier. So, very simply put, I'm going to draw a curve, an input-output curve for a transistor. Notice that in this section right here, in between those hashes, that's basically linear. This is cutoff. And this is saturation. Well, when you're in saturation, it doesn't matter how much more you add. You're not going to add anything to the output. That's not a linear function. A linear function is if I put in a certain amount of input, I get a certain amount of output. If I change that to twice the input, I get twice the output. That is how a nice clean amplifier works if you're trying to make somebody's voice louder, right? Well, if I'm in cutoff for that first part, it's definitely not a line, it's a curve. Up here in saturation, this is a curve. So when I am using an amplifier that requires nice, clean amplification, like is used in single sideband, I have a switch that allows me to switch to single sideband. So I use the linear portion of that transistor's range. For FM, it doesn't really matter because you're just amplifying a frequency. It doesn't matter if it's big or small. You're just using the frequency. But for voice, for single sideband or for CW, it does matter. Or for single sideband, it does matter. Okay, so now I'm going to talk very quietly and tell me, I'd like you to raise your hand if you can hear me talk. Ready? 3, 4. What was the first number you heard? 3.
4.
Okay. Okay. I went I started almost silently and then went up. That's a measure of sensitivity. If you could hear me when I was saying 1, that means your ears and your computer are very sensitive. It's the same thing with a radio. The more sensitive it is, the quieter the signal you can hear. Now, on the count of 3, I'm going to ask everyone who's unmuted to say your name. I'm ready. 1, 2, 3.
Howard.
Aaron.
Okay, so the ability to pick out one particular signal out of that mess, that's known as selectivity. If somebody came in with a higher pitch or a lower pitch, and I could filter it out, that would be selectivity. If you're going to install an RF preamplifier, it's important to note that, kind of like we drew yesterday, you can't amplify what you can't hear. So if you're going to try to recover a signal that's really weak, you want to put your preamplifier as close to the antenna as possible. A device used to convert one signal to another frequency, that's known as a mixer. The mixer is at the core of a transverter. A circuit that generates a specific frequency, well, we have that thing called resonance that requires capacitors and inductors to be picked. If you pick those, then you can actually build a circuit that can either operate as a filter, or if you drive it into oscillation, it becomes an oscillator and it oscillates at a particular frequency. That's known as an oscillator. That provides us a signal, a synthesized signal that we can use in other parts of our equipment. The combination of an RF carrier signal with something like speech, that's known as modulation. So if we have a modulator and on the other side of it, we have to take it apart, that's called a demodulator. Modulator, demodulator, you take those two words and push them together and you get something called a modem. If anyone's ever heard of a modem, that's where the word modem comes from. Modulator, demodulator. Okay, and we're still talking about symptoms, causes, cures, and common transceiver and receiver problems. Most things that we talk about are either going to result in or cause interference or distortion. So fundamental overload in a receiver means that there's a really big station nearby that is just completely wiping out your receiver. You can't hear anything because all of the energy in the receiver is being used on that one signal that's really nearby.
It's all the rednecks that's got the linear amps.
Yes. Harmonics. A harmonic is a multiple of a frequency. So if I'm on 7 megahertz, a harmonic would be 14 or 21 or 28 or 35. Those are harmonics. Harmonic interference can interfere with lots of other things. A spurious emission is a frequency that is not harmonically related, but is also unintentional. So your transmitter, if it's not tuned properly, you might be desiring to put out a signal on 7 megahertz, but you're also putting out one on 11, which has nothing to do with the 7 megahertz. That's known as a spurious emission. All of those things are bad. If your neighbor tells you that your station's transmission are interfering with a radio or TV, first thing to note is that if you have a ham license, the assumption is that you know what your operating requirements are as far as spectral purity and things like that. You're basically licensed to transmit a signal. If you can verify that you're doing your part per part 97 of the FCC rules, then it becomes a not my problem. So if I'm interfering with the TV next door or something like that, it is a not my problem, but I still might want to help. If that's the case, we might want to install a filter, or at least, well, first thing to do is make sure your TV is working fine. That means that, okay, well, it really is their problem, and I'm going to go try to help if you feel like helping. A licensed service always takes precedence over an unlicensed service. Part 15 is like a computer or an iPad, which has oscillators in it. Those things can generate radio frequency energy. If anyone's ever had put their phone next to their computer, headphones or something, you can hear it going do 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 sometimes. That is RF energy that is being generated by your phone that's being picked up by your headphone. A Part 15 device is an unlicensed device. It can't interfere with any licensed services, and it must accept interference from licensed services. So let's say your neighbor put in some grow lamps for their new pot grow. I live in Oregon, happens all the time. So they put in new grow lamps. They bought they brought cheap grow lamps, and the grow lamps make all kinds of RF interference to you. It is their responsibility to do something about it if it's interfering with your ability to operate your station. Similarly, if when you transmit, their grow lamps brighten and dim, that's not your problem if you're operating legal. Okay, non-fiber optic cable TV interference. Connectors always have a way of going loose. So always snug up the connectors if your cable TV is acting weird. A broadcast AM or FM radio can receive a ham radio station if the cheaply made radio that you're listening to is poorly made and is unable to ignore those signals that are nearby. That is known as fundamental overload. If you really want to fix that, and it's on a different frequency, you can install a filter on that other device to block the signals that are causing problems. If you have let's say I have a legally operating 2-meter radio like this, and there is an FM radio station on 107.3 right next door, literally right next door to me. I might actually still be receiving on my ham radio that FM radio station anywhere I tune. It might be impossible for me to get rid of it. So what I might do then is on this radio, on my handheld radio, between the radio and the antenna, I would install a band reject filter that would block FM radio. That's known as a band reject filter. If your neighbor's home, something in your neighbor's home is causing interference to your station, well, okay, you're within the law because you have the legal station. Make sure that your station is operating properly and then go tell your neighbor. And then maybe help them go find it. I actually had this happen once. I had a neighbor with a cordless phone extender system that used the house wiring as an antenna. Or, well, not intentionally. It used it to connect things together, but house wiring at 3.5 megahertz makes a really good transmitting antenna. So they were transmitting all of their phone calls around the entire neighborhood. And when I told them about that, I figured out who it was because they were on the phone. And I said, call me and I'll play it back for you. And they said, oh, we could probably get rid of that. So they happily got rid of it. What can be a problem if your FM radio signals are distorted or unintelligible? Well, if your batteries are low, if you're in a bad spot, if you're talking too loudly, if you're off frequency, those can all cause you to be distorted. If you get RF feedback, that's literally a case of your system has wires in it. I have my computer attached to my radio. So like I have my computer attached to my radio, attached to my antenna, and there's multiple wires connecting the computer to the radio. And the computer directs the radio to transmit, and some of the RF energy, because I'm in the vicinity of the antenna, actually gets carried back into the computer over the wires. Well, if I'm lucky, I'll sound distorted or garbled. What actually happened in my case was that my computer would actually lock up. The RF energy would get back into the computer and cause it to lock up the computer. I would have to reboot the computer.
They had an unshielded computer cabinet.
I did unshielded. No, I shielded computer cabinet, but unshielded cable. So how do I fix that problem? What did I put on the cable?
Ferrite bead.
Ferrite bead. Yep, ferrite choke. And in fact, in order to solve the problem, I needed 5 of them. I just kept adding them until the problem went away.
But I guess you could do that.
Yeah, it works.
And they got like little plastic clip-on things. You just
That's what I have. I have 5 of those. Now you could also, if you had access to it, if you had a big enough one, you could just take it through a big donut and wrap it around like 5 times. And that would work really well. If you're told that your handheld radio is over deviating basically means that your signal, which normally fills up a certain amount of space, suddenly fills up more. And since no one's listening to anything outside of that area that it's supposed to be listening to, Like, let's say that this is the block of frequencies that you're supposed to be transmitting in, and you're speaking too loudly and your signal is basically going from there to there. Well, nobody's listening to this, but that's part of your voice, right? That has information about you, which basically means that all of a sudden you're kind of not understandable anymore. Your signal is getting distorted. This is known as over deviating.
So what does that sound like? A muffled sound?
Yeah, or yeah, I mean it's FM, so basically it just sounds like distorted audio. So in order to fix that, because you typically don't have a microphone gain control, you typically just back away from the microphone. All right, using basic test instruments. Okay, so now we're going to get into test instruments. So we're going to go back to our schematic, which we drew yesterday, which looks like this. So here's our schematic. Everybody remember this really yesterday morning schematic? So
Yep.
we had our battery, we had our resistor. Okay, now the couple of things we want to be able to measure. A multimeter measures volts, ohms, and amps. Those are the three really cool and important things that we would want to measure. So in order to take a measurement of voltage, we would take our voltmeter and put it like that in parallel with something. That measures the difference between that side and that side. That's a voltmeter. If we want to measure how much current we have, well, that's a little bit different case because current needs to flow through something. What we have to do in this case is we have to take an ammeter and stick it in series so that all the current that's flowing through here also flows through the ammeter so it can be measured. If we wanted to measure the voltage across a resistor, again, we would put a voltmeter across the resistor. But now let's say that instead of wanting to measure voltage, we had a resistor that was an unknown resistor. We didn't know what we didn't know what its number of ohms was. Well, how do we do that? Well, we could measure the volts and amps and take care of it that way. Or we can draw our circuit back the way it was. And what I'm going to do is ask you the problem with this. What is the problem with this circuit? The problem is that the way that an ohm meter works is by taking a resistor, an unknown resistor. What it has in it is a battery and an ammeter. This is an ohm meter. This is how an ohm meter works. It takes a voltage, measures the voltage, and then measures the current and uses Ohm's law, E equals IR. R is equal to E divided by I, and it calculates the E and the I to give you an answer for resistance. So now the question that I have is, if you have a resistor that's in a circuit, do you see a problem with this? If you
Yeah,
want to
can't
measure it.
resistance because now you have two batteries.
That's right. Now you have two batteries, and at best, your resistance will be wrong, and at worst, you're going to blow up your ohm meter. So what you would typically do is you would break that line, at least in one place, and just measure it like that. So you'd actually have to take the circuit apart. And the easiest way to do it is just remove the resistor from the circuit so you can measure it and then put it back in. Okay.
Other stuff in parallel with the resistor as well.
Yeah, we're getting that. We're getting there. Yeah. So if there's other stuff in there, the reason to take it out is because there might be other components that you didn't expect. So now let's look at this. We have an ohm meter. So this is an ohm meter. And we are measuring some black box. We want to know what the resistance of this black box is. And what we see is that when we connect it, we get a resistance that looks like 0 and then goes up to infinity. So in other words, our resistance over time starts at 0 and then goes like that. And then it says infinity. This is an indication that there's a capacitor in the box. Because what happens to the capacitor is that at first, there's a ton of current flowing into the capacitor, charging the plates of the capacitor. But then it gets full. So at first, there's a lot of current. A lot of current by Ohm's law says it's a really low resistance. So the resistance starts at 0, but then once it's fully charged, it goes up to infinity. So if you have something that looks like this over time, that means that you're actually looking at a capacitor in the circuit. Okay, another one is what can damage a multimeter. Multimeters have a given rating. If you try to measure voltage when using the resistance setting, that'll do it. There's usually, if you're lucky, there's maybe a fuse in there that you'll blow. Done that. Another thing that can happen is that multimeters, you would never really want to use it to measure too high of a voltage than rated. For instance, since I work in industry, my meter that I have is rated for, let's see, I've got this meter right here. Come on. Notice it's a $450 multimeter. It's rated for 1,000 volts. Now, I could also go to Harbor Freight and get a multimeter, right? The very cheap one they have is about $3. Sometimes they even give it away for free. Now, if I'm going to be going into a mill and I'm going to be measuring, oh, look, $6. Okay. If I'm going to be going into a mill and measuring, even though this says it's good for 250 volts, I'm not going to be measuring 250 volts with this meter. You know, with my $500 meter, I'm going to check my leads. And so long as my leads are good for it and the meter's good for it, I'll be okay measuring 1,000 volts. You know, I would be okay doing that. So your meter has to be rated for the thing that you're measuring. Okay, I think we pretty much covered everything else there. Increasing resistance with time, electric current. Okay, soldering. We only use rosin core solder. Do not use acid core solder. This says which should you not use. Don't use acid core. Acid core is for plumbing. A cold solder joint is not smooth. It basically means that the solder melted, but the actual devices that it was being stuck to didn't get hot enough to actually flow the material, and it will stop working at the most inopportune time possible. Okay, FM. This is what we use on repeaters. How to do this on FM? A repeater station is an automatic station that retransmits signals coming in, going out. Automatic stations, those are under automatic control, repeater, auxiliary, or space stations. A space station is anything 50 kilometers up or higher in the air. So that's the dividing line. An auxiliary station is maybe like a station that is set up as a microwave link from point to point. It's never designed to be used by a person. It's just basically designed to take a signal and forward it from one repeater to another. This can be something that you'd find in a linked repeater system. A linked repeater system is, we have one in Oregon with over 50 repeaters linked together so that if you transmit into one, your signal goes out in from all of them. It covers the entire state and then some. A common repeater offset in the 2 meter band is plus or minus 600 kilohertz, which we talked about. On the 70 centimeter band, it's 5 megahertz or 5,000 kilohertz. Subaudible tone is known as CTCSS, continuous tone carrier squelch system. It's also known as PL or private line, Motorola trademark. If you can't be heard on a repeater, but you can hear the repeater just fine, you might have the offset set wrong, you might have the tone set wrong, you might have the DCS set wrong. Interestingly, we have a beginner's net here every Monday night in Eugene. We come up with these 3 things all the time. Do you have your offset set right? Do you have your tone set right? You're transmitting on the repeater output. You have it set backward. There's a transceiver reverse function that is basically allowing you to reverse the functionality of your transceiver so that you're listening on the repeater input. The reason to do that is because you might be trying to hear that person down the street who has their radio set up wrong. When would you sound distorted? If you're talking too loudly. How do you call another station? Let's see. Do we still have? Oh, he left. Okay. So basically I would call another station by giving their call sign and then my own. So I'd say like W7PL N7JI. That would be me calling them. Now, I could also just say, hey, I'm here. I would just say N7JI monitoring or N7JI listening on frequency. If you're on the same frequency as the other person you're talking to, that's known as simplex. Why would we ever use simplex? Because let's say that you and another station are only a quarter mile apart. There's no real reason to use a repeater if you're in mutual communication range. If you don't need anybody else to hear what you're saying and you're a quarter mile apart, you don't need to tie up a repeater because a repeater is a resource. Other people might want or need to use it. A band plan is what we'd call a gentleman's agreement, that if you look at the band plan that we were looking at yesterday, you will see that there are certain areas of certain bands that are set aside for certain activities. There are space, for talking to satellites. There's room for simplex communications. There's room for duplex communications through repeaters. There's space for weak signal, which is single sideband. Those are set up to keep the peace. The national simplex calling frequency, which is basically like, used everywhere in the US and Canada as kind of like, if you're going to be going into an area that you don't know where the repeaters are, everybody listens to 146.52. That's our national simplex calling frequency by everyone's band plan. Okay, on the high frequency bands, CQ, we would never call CQ through a repeater. This is just by convention. So don't do it. If you're going to be listening on a repeater, just say N7JI testing, N7JI listening, or whatever your call sign is, and then listening or monitoring. However, if you're on the high frequency bands, you're basically shouting off into space. There's no expectation of there being a repeater there. So your signal is just basically going off and hopefully going to be picked up by somebody. The 2 letters we use are CQ, literally seek you. I'm looking for somebody to talk to. CQ means I'm calling anyone. How do you respond? So if you hear CQ, 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 and then a call sign, I would give the other station's call sign. Like if I heard CQ, CQ, this is W7 Papa Lima, I would respond, W7 Papa Lima, this is N7JI, over. When identifying your station, even when making test transmissions, you have to ID, however that means. If it's Morse code, if it's using voice, whatever's legal to use in that particular part of the band, that's how you identify the station. You have to identify your station every 10 minutes and at the end. of the communication. Notice you do not have to identify your station at the beginning. This is one of those things that I've learned that is different between the United States and Canada. If you're operating in Canada, which you are categorically permitted to do, you with a US license, you just have to sign your call sign appropriately. You have to follow the Canadian rules, which means you have to know the Canadian rules. But in the US, it's every 10 minutes and at the end. Q signals, we use Q signals all the time. The more you use radio, the more you will enjoy Q signals. They basically are canned messages for getting a lot of information across in a hurry. QRM, that means I'm being interfered with. Or as a question, are you being interfered with? And then QSY means let's go to another frequency, or as a question, would you like to change to another frequency? There's QTH. QTH is where you are. So the Q signals came out because there are not that many words that start with the letter Q. So there were always a lot of Q things available. And canned messages came out of telegraphy because it was a lot easier to send a 3-letter code to explain something than to send an entire sentence. A band plan, again, is a voluntary guideline for using different modes or activities within a frequency band, just to keep the peace. And it's a voluntary thing, but people typically will follow it. When 2 stations are transmitting on the same frequency, neither one owns it. It's very important to note that nobody owns a frequency. We're all just sort of like users of the national park. Nobody owns a frequency. So they have to negotiate it. This might be a case of somebody saying, well, we're about to run a net and we have people from 17 different states that join, and we typically get 60 people here. And we've been doing it every day for the last 50 years. Would it be okay if you moved so we could do it here? The answer doesn't have to be yes, but you should probably say okay. Amateur Radio Emergency Service, ARES. This is an organization that is a volunteer organization that uses radio and people who are licensed to provide emergency communications. It stands for Amateur Radio Emergency Service. RACES, RACES, is specifically a group of hams, very much like ARES, that have registered with their local governmental agency to provide communications. So they're actually listed not just as volunteers, but they're actually, working on behalf of a civil agency, of a governmental agency. That's the big difference between RACES and ARES. For the most part, they can do the same thing. Notice that RACES says it's a Part 97 amateur radio service for civil defense communications during national emergencies. So basically, ARES is a volunteer group. RACES is a volunteer group, but it's specifically coded into the amateur radio rules.
So is that RACES that's official?
Yeah.
And
So-
whereas the ARES is unofficial.
Well, it's official, but it's volunteer. In other words, like there are a lot of ARES groups. I mean, ARES is a national program, and it's just that RACES is the next level up, specifically for civil defense. ARES can be, it's not necessarily even national emergencies. It could be anything. It could be a local wildfire. So RACES is typically going to be something that's bigger and more official.
So do they RACES, are they part of the civil air people as well?
Civil Air Patrol is a different group.
That's a different group.
Yep. Okay, let's see. Net control station. Net control is somebody who runs a net. A net is short for a network of people who are gathered together on a frequency to transmit information from place to place. The information might be, hey, I'm just telling you I'm here, or the information could be health and welfare information about, flood victims. Or we need a fire truck. So net control station is the person who is the center of communication. So basically calls the net, dissolves the net, and controls all the traffic going back and forth. Traffic is what we call information that is going back and forth within a network from person to person. And it is important to understand, if it's a directed net, like many nets are, that you basically don't talk unless you're asked to talk, because everybody's using the single resource, which is the network. And unless you have something really important to talk about, if you're talking, then somebody else can't. And they might have information that's more important than you. Traffic is messages that are exchanged by stations. Good traffic handling, that would be passing messages exactly as they come in. So there's something called a check. A check is a count of the number of words or word equivalents that are being transmitted across in a message. It's very important to have an exact check. Let's say I am going to the zoo. That would be 6. Okay, I am going to the zoo with a check of 7. Uh-oh, we left something out. Well, maybe the message was, I am not going to the zoo. That's a totally different message. So if you get something that doesn't match, the check and the number of words don't match, you need a repeat. The other thing is that, let's say that the name Dare, right? Well, let's say that you want to make sure it's spelled properly. So across a network, accuracy is very important. So my message would be, for instance, the name is Dare. I spell Delta Alpha India Romeo Echo. That takes away all ambiguity. I'm using phonetics to make sure that it's understood, that it's something that I want to get across. Let's see. What information is in the preamble of a message? A message is basically a formal piece of traffic information that's going from place to place. The preamble is who it's from and who it's to and when it was sent. Okay, so when do FCC rules not apply to operation of a ham station? And the answer is they always apply if it's in the United States or on a boat that is registered in the United States. The FCC rules always apply. Now, when are you allowed to violate the rules? Well, you're allowed to violate the rules in cases of 2 different things: immediate safety of human life, protection of property. You will always find those 2 exceptions. But since that's actually in the rules, you're still following the rules. So basically, in case of immediate safety of life or property, that implies you don't have to follow the rules that you know to be the rules. You might have to explain what happened later, but you're still going to be okay. Amateur satellite operation. Well, a space station is anything 50 kilometers or higher. So a satellite is something that is basically floating around. It could be geosynchronous, which means it's always over the same place on Earth. Again, there's that Qatari satellite, which is up at 22,000 miles, which is geosynchronous over the Eastern Hemisphere. And then there are a lot of low Earth orbit satellites, which are typically between 200 and 400 miles up. They have different shaped orbits. They have different periods. But one of the fundamental things about these satellites is that they are in low Earth orbit, or LEO. They're known as LEO. And because they are in low Earth orbit and they're not geosynchronous, they actually go around the Earth anywhere between every 90 minutes to every 2.5 hours or so. Which means that we might not get to hear the International Space Station go overhead for a period of 14 hours. But then we might get 7 straight passes where it goes overhead over a period of 9 hours. Anybody with a technician class or higher license can talk to the International Space Station or any other repeater that is using the bands that you're allowed to transmit on up in space. any other satellite carrying a repeater or, anything that's using a band that you're allowed to use. And since technician license can transmit on 50 megahertz and up with full privileges, a repeater that is on the ISS using 70 centimeters, which is 440 megahertz, or 2 meters, which is 146 megahertz, you can use those. Even if, let's say that the satellite is retransmitting signals on some other band that you're not allowed to use because you don't have privileges there. If you didn't put the signal there, you're okay. Okay, up a satellite that's operating in mode UV, that's UHF up, VHF down. That's the pattern that it follows. So UV is UHF up and VHF down. That's usually 70 centimeters up and 2 meter band down. Effective radiated power on a satellite uplink. Okay, so not all satellites are going to be FM satellites. Some of them are single sideband satellites. All satellites will actually transmit an ID, like the repeater on the space station transmits the ID NA1SS because that's its call sign. It's a ham transmitter. It has to identify. Part of what they do is they beacon information down to the ground. They send out health and status information about the satellite. They also send out call signs. Well, if you can hear yourself and you're louder than the beacon, that means you're using too much power. That means you're blocking other users from getting into it and using the satellite. So use just enough power. This is one of those places where it's really important to note and be able to hear exactly what you sound like. Again, low Earth orbit, LEO is LEO. That's a low Earth orbit satellite. A satellite beacon sends out a call sign. It sends out health and status of the satellite. So we are at 216 miles above the Earth's surface. The temperature on board is a balmy 72 degrees Fahrenheit. And our transmitter is in good shape. Our battery voltage is 16 volts. Everything's happy. Or it'll tell you that, that there's a certain transponder that is not working at this time. So that's satellite beacon information. Anybody can receive information from a satellite. You don't need a ham license to listen. So if a satellite's traveling overhead, you don't need a ham license to listen to it. A satellite tracking program. So, okay, what I'm going to do is I'm going to go to, AMSAT. This is the Amateur Satellite Corporation, the Radio Amateur Satellite Corporation. This is a bunch of hams whose job it is and whose volunteer task it is to put satellites from hams into space, help them build it, help them get a ride. One of the things that this site does is that it provides a pass predictor. So essentially, the Keplerian elements for a particular satellite are programmed into their system. Let's say, let's take a look at the next 20 passes for my grid square and go. Here are the next 20 passes for the International Space Station. Here is the current and future location of the International Space Station. These are calculated from something called Keplerian elements, named after Johannes Kepler. You program the Keplerian elements into a satellite tracking package, it'll be able to predict where the satellite is at any given time.
That's pretty slick.
It's really cool. It makes it a lot easier to track a satellite. And then, for instance, when the satellite is going to be, let's look at a good pass. Maximum elevation. There's a good one. 77-degree elevation. That's almost directly overhead. It says that for my location, acquisition of signal will be west-northwest. loss of signal will be southeast. So it'll go almost directly overhead. The time that it shows up is 6:40 in the morning tomorrow morning, and it's an almost 11-minute path. That's a good long path. So if I wanted to try to work through the ISS, that would be a good time to do it. Now, the other question is whether or not the ISS repeater is up and running. Let's see. I know there's a repeater status. Current status. So I use service module configured, etc., etc. So this is amateur radio on the International Space Station, or ARIS. So there are a lot of resources out there for those of you who are interested in satellite communication. All right, next, Doppler shift. We mentioned this a little yesterday. As satellites are moving across the sky, especially the low Earth orbit ones, the higher up they are, the lower the speed. The lower they are, the higher the speed. So a satellite like the ISS at 220 miles up is approaching us at 17,000 miles an hour when it's down on the horizon, and running away from us at 17,000 miles an hour. I'll let somebody else get it. So as it is approaching us and running away from us, that is actually moving fast enough that it actually compresses the wavelengths as they're getting nearer to us and stretches them out as they're on the way out, which means that if we're if we're trying to communicate with a satellite, we actually have to account for Doppler shift. There's also something called spin fade. Spin fade, because satellites, in order to stay in orbit, they typically will tumble and rotate. If an antenna is pointing at you and then it is suddenly pointing away from you, you'll notice it disappear. That's known as spin fade. Other operating activities. Hey, as contesting is making lots of contacts over a specified period. I like to participate in the 24-hour ones. I also like to participate in the 1-hour ones because they don't take as much time. If you're doing a contest is all about efficient operating. If the exchange is your name and your state, then unless I know the person I'm talking to really well, I'm just going to say Scott in Oregon, over. Or just Scott in Oregon, Scott, OR. And then the other person will do the same thing. So you just follow the rules of the contest. Minimum exchange for proper identification. A grid locator. So this is one of those things that I believe I included in the packet that I sent out. Maidenhead grid locator.
Where'd my mouse go?
So here is, oh, come on. Not so good at typing today. Okay, Maidenhead grid locator map. There we go. The entire world is split into 20 by 10 degree blocks. Those are big grids. And then within each of those, each one of those is split into 10 by 10.
And why is it called Maidenhead?
I think it's from location in England where it started.
Oh, okay.
Not 100% sure. But basically it's those large blocks are 20 degrees in latitude by 10 degrees in longitude. And each of those is split up into 100 grid squares, small grid squares, which are each 2 degrees in 2 degrees in longitude by 1 degree in latitude. The reason that we do that is because if you look at England, for instance, 1, 2, 3, 4, 5, 7, 8, 9, 10. The United Kingdom has, I don't know, something like 50 grid squares, as opposed to just pointing to England. Let's say that you're in France. France is right across the channel. If you're pointing to England or pointing to the United Kingdom, that could actually be pointing to a lot of different places. So it's really particularly useful if you're operating on VHF or UHF as far as figuring out where you're supposed to be pointing. That's known as the Maidenhead grid square map.
And that does what for you? Just enables you to point your antenna?
Because let's say that we were to look at, let's say we're looking at the United States. I hope this comes up. Come on.
Well, you had the one you sent us.
Yeah, there we go. Okay. So if we're looking at this, notice that all those grid squares, like Montana is pretty darn big, right? What it allows you to do is get a little more granular and point at a different location. So if you're in Maine and you're pointing to Oregon, there's not a problem pointing your antenna. But if you're in Washington and you're pointing to Oregon, it could be almost due west, almost due east, almost due south, or anywhere in between. So this is just
Is there a calculator, azimuth calculator for that?
Sure.
Where you can type in the number square from one square to another and it tells you which way to point?
right there. Grid square locator map. It'll tell you what your heading is.
Huh.
Let's see, radio direction finding. We also call it fox hunting. Here in Eugene, it's bunny hunting or duck hunting. Radio direction finding is basically using receivers and directional antennas to point around and figure out where the hidden transmitter is located. So if you are into search and rescue, let's say with ski patrol or something, and somebody has some kind of radio or a cell phone on them, and you can pick up the signal, this allows you to find the hidden hiker or find the hidden skier who was covered by an avalanche. Okay, IRLP, Internet Radio Linking Project. IRLP uses VoIP, which is voice over internet. Voice over internet is a technique for sending digitized voice over the internet where it can be switched and routed and moved from place to place. Echolink. Echolink is a cell phone or computer-based application where what you do is you send in to the Echolink people an official copy of your license. And what they do is they create an account for you such that once you have that account that says this is your license, you can go from your cell phone or from your computer anywhere where you have an internet connection and connect to any other person using that system or any other repeater that is tied to that system, and use that repeater or talk to that other person as though you were using that repeater locally. The nice thing about this is when I travel, I can pull up Echolink on my phone. I can connect to our local repeater and participate in local Eugene area communications as if I were still in town. So that's Echolink. IRLP. How do you connect a radio to IRLP? Well, everybody who has a handheld radio has probably noticed at some point that it has this nice little touchtone pad, right? Well, we don't really think of it as a touchtone pad. We think of it as for programming a frequency. But you know what? It actually is a touchtone pad. If you are transmitting, if you have the push to talk button down and you push one of those buttons, you will actually get a touch tone, just like your old touchtone phone. So if you know the sequence, you punch in the right code, you will potentially connect the radio or connect the repeater to the internet, at which point it becomes a linked system.
Huh. Because those touch tones, are they the same as the phone company uses?
Yep. It's called, they're known as DTMF, which is dual tone multi-frequency.
That's pretty cool.
Yep. Okay, what type of signaling use? Oh, in fact, that's the next question. What type of signaling uses pairs of audio tones? DTMF. right? We used to use it for our telephones. We used to actually have DTMF generators in all our phones. Now it's all synthesized, but the radios do the same thing. An amateur station that connects other amateur stations to the internet is known as a gateway. Okay, here we go. My most and least favorite part. So you know what? It's time for a 5-minute break. Everybody good? 5-minute break. I told you the hard stuff was yesterday. This is all just rules and regs.
Well, you gotta memorize all this crap though, don't you?
Yeah, but once you got it memorized, it applies to any license class.
Oh, okay.
You know, I mean, the rules and regs are the rules and regs.
So it's the same
The
for
same stuff.
the low guy as it is for the high guy.
Yep.
Huh.
All right. Break time.
Oh, how cute.
Hello, hello.
Howdy.
Hey. All right. So, Carol, you're muted.
Yes,
Is this making sense?
some.
I mean,
Tom?
this part is definitely easier to get than the other.
Like I said, this is the easier part.
Yeah.
It's the rules and regulations.
Yeah.
So,
Who doesn't know rules, right?
right.
Gotta learn them no matter what you do.
Well, this is, but this is why I say that, if you're going to go for your general, it's really not all that different. It just comes down to specific things that are required for one license class versus the other. But radio theory, antenna theory, they're the same, independent of anything else.
So it's just basically take both exams at the same time.
Well, it's still got to do them in order, but yeah. I mean, I know a lot of people who do that. I mean, or you could do one month and one the next month,
So on the general, how many math questions are there?
It's a little more. I mean, but the nice thing is that you can study for, and I mean, you can do what my kids did. They memorized the whole thing.
Yeah, I'm sure their brain is a little bit more agile than
Well, my now 15-year-old, he memorized the technician exam and he memorized the general exam, and took him 3 shots on the general, but he got it. And Hannah memorized the technician, and she understood a little bit better. She'd taken physics, but she memorized the technician and she memorized the general. And then I said, okay, for another $200, I dare you to do the extra exam. So
did somebody accept the dare?
Yeah, Hannah did it.
Oh,
She
cool.
took it. She got her extra. She actually, when she turned 18, she became an examiner that day.
Wow.
She actually gave a license exam to her physics teacher. Ellie, Asher?
Yeah,
She,
yeah.
she gave Asher his license exam and graded it.
Oh, that's hilarious. I took physics from him.
Uh-huh.
She better have passed him.
He did.
Now you can mess with people.
Well, she went. Well, she when she went over to him and said, "Well, you passed." I mean, this is just after their senior year ended. It was kind of funny. Okay, everybody ready? We're getting into that home stretch, rules and regulations. And this is a lot of definitions of things. Definitions of
No.
This is definitions of what governs what we can do and what we can't do and why. Okay, the FCC, we're in the United States. The FCC is the Federal Communications Commission. They govern amateur radio rules in the United States. If anyone is curious to see what those look like, those are FCC Part 97. The FCC maintains a copy. The ARRL, obviously being the National Association for Amateur Radio, maintains a copy. Notice it's part of the federal regulations, and here it is in this format. It is obviously somewhat dry, and because it's rules, you notice it's a little bit lengthy.
Hey, that looks like a government document.
That is a government document right there. That is the part that is the searchable, however, FCC rules. One of the things
I always had to refer to the government register when I worked to look up changes. That's kind of like that.
Uh-huh. Okay, so notice this basis and purpose. Actually, this is really kind of important and profound, because as of starting in the 1930s, these rules are basically unchanged as to why we are allowed to exist. I mean, if you think about it, the FCC and the government, they don't really give away that many things for free. I mean, we basically have access to these frequencies all around the world by international convention for free. Well, you got to get something for your, investment. So, okay, recognition and enhancement of the value of the amateur service to the public as a voluntary, non-commercial communication service, particularly with respect to emergency communication. That is one of the 5 rules, one of the 5 things that we exist for. Continuation and extension of the amateur's proven ability to contribute to the advancement of the radio art. Radio is actually still developing. It is a living thing. Encouragement and improvement of the amateur service through rules providing for advancing skills in communication and technical phases of the art. So when you go and you figure out how to build an antenna, that's meeting part C. Expansion of the existing reservoir of trained operators, technicians, and electronics experts. By virtue of going through this class, when you go to take your exam and you know something about what you're doing, you're trained operator, you get to fix stuff, you become a trained technician. Electronics experts, if you start building antennas, you start building circuit boards. There's a lot of hams who are part of the maker space and hacker space. A lot of good programmers who have their ham radio licenses because it's the communications toolbox that doesn't exist anywhere else. So they want to be able to do long range communications with the inventions that they've come up with. This is where they go. Continuation of the extension of the unique ability to enhance international goodwill. We are part of an international family of over 3 million operators worldwide, of which about 750,000 live in the United States. There's over 1 million in Japan, but most countries in the world have hams, with the exception of North Korea and one of the stands. I don't remember which one it is. I think it's Turkmenistan. It's one of the stands. It's legal all over the place, but they don't necessarily, their particular governments don't necessarily participate. But notice that it says international goodwill. I have in my box of cards, if you think about countries that the United States has at times not been on that good of terms with, right, as a government. Well, you think about the Cold War. I got my license in 1985. Was it 1984? 1984. The Cold War still had the Soviet Union in existence. There was Germany, West Germany, and East Germany. There was Czechoslovakia, Romania, Bulgaria, Hungary. The Baltic states were part of the Soviet Union. So was Ukraine. So was Kazakhstan. Those all the people who lived there, however, I have lots and lots of cards from lots and lots of people in all of those places because it's a non-commercial, non-political thing. So when I actually went in for a security clearance at my first job, one of the things they asked was, have you had contact with anybody from any of these countries? And there were like a whole mess of them with which I'd had contact with. And I said, yeah, this one. And there were like 20 of them that I said yes to. I said, okay, in what capacity? I said, ham radio operator. And the guy who was interviewing me said, oh, you're fine. Because it's understood that if that's why you were in communication with them, that was part of the international goodwill thing. Okay. Let's see, definitions. We're going to go away from that. We're going to go back to here. Okay. So those are the reasons we exist. Okay, a beacon. A beacon is a one-way transmitter that sends out information either for informational purposes like measuring weather and sending it back from a mountaintop to another station, or for looking at propagation. So basically, if we've got a signal that's coming out of a mountaintop in Nevada, it's just sending out a beacon saying where it is and here's its power level. If that beacon is heard in any of these other places, that's an indicator that there's an open propagation path between the two places. So that's the purpose of a beacon. A space station, again, anything 50 kilometers or higher above the Earth's surface. When are you allowed to perform willful interference? That means you're doing it on purpose. The answer is never, even if they're really making you mad. Just learn to turn the knob. You know, you can always pick another frequency. Spin the knob. Transmit and receive channels for auxiliary and repeater stations. Okay, so what we're going to do is I'm going to pull up the website for the ORRC. At least I think it is. The Oregon Region Relay Council. So this is for the state of Oregon. We have in the state of Oregon the ORRC, which is a volunteer organization that has set up band plans in the state of Oregon. This is typically going to be harmonized with all the other states nearby. Now notice we have frequencies and number of channels allocated and what they're to be used for. That is basically to keep the peace within the state so that people who are operating on this band within the state, because we're still limited as far as bandwidths, what we can do. Let's look at another band, 70 centimeter band. Oh, look, 425 to 431. Amateur television. We actually have a TV channel that we can use. Same thing on 33 centimeter. We have ATV. There's a TV channel. Actually, 2 TV channels.
Anything good to watch?
No, just us. It's just, but you can, you know, if you have your own equipment, you can send out a TV signal. 6 megahertz wide high scan TV. Published coordinations. These are all the repeaters in the state of Oregon. Now they have to be coordinated because you'll notice that on certain frequencies, there are multiple repeaters like 146.72. There are 2 of them. One is in Junction City. This is the one that I'm responsible for. Oh, look, there's me. Another one is in Astoria, which is up on the northwestern Oregon coast. They have to be coordinated because they share a frequency, and geographically, they might be interfering with each other. So if there was another one, let's say somebody wanted to put up a repeater halfway between us, they would have to go through this group, and the group would look at it and say, no, that'll never work. Let's pick you a different frequency. Or if a repeater decides that they're going to be dismantled, then we can assign you this one. So they're the ones who are responsible for keeping the peace. So that is a volunteer frequency coordinator. And all amateur operators in a local or regional area whose stations are eligible to be repeater or auxiliary stations can vote for who they choose to be the coordinator. It's a thankless job, but somebody's got to do it.
Are you one of them?
I am not. I am not. I as of 2 days ago, I'm actually the Oregon section manager, which is another thankless job.
So you coordinate the coordinators?
Not these guys. That's a different group. I am now I'm now the ARRL section coordinator. And that means that the ARRL, which I might as well put it up now that I brought it up. So this is the National Organization for Amateur Radio. This is, there are 700, let's say 750,000 hams in the United States. And sorry, I have to do this to get in.
So you get a text message on your phone?
Yeah.
Oh boy.
Yep, two-factor authentication. Okay, so the ARRL is the National Association for Amateur Radio. It's basically, it's a ham-run organization that provides training, licensing help, books. They're the ones who run ARES, which is the Amateur Radio Emergency Service in the United States. They published QST magazine for a long time. They have other publications. They coordinate contests. They do all kinds of cool stuff. One of the other things they do is all of those I guess you'd call all of those features that are provided by the ARRL are provided on the national level, and they're supposed to be on the state level. They're supposed to be organizers who help out with, with emergency contacts, with education, with educational programs, with technical expertise. If someone needs help, if they have a radio frequency interference problem, stuff like that. So I'm basically responsible for all of those services and being the interface between the national office and everybody in the state of Oregon.
Oh, if somebody don't like what people are
They come to me. As of 2
doing,
days ago,
come to you.
as of 2 days ago, they come to me. I haven't gotten any nasty grams yet. But so
Still
the
young.
there's lots of time. One of the other reasons for this organization to exist is that how much do we pay to use these frequencies that we use? We use nothing, right? We pay nothing. We provide services, we provide emergency communications, we provide all kinds of training, but we don't give them government any money for all of these.
Yeah, and they want our frequencies.
That's
too.
exactly right. There are many, many different groups of people who are very well funded, who will frequently grab all their lobbyists and go lobby Congress to lobby the FCC to give them frequencies, many of which we are presently using. So if for no other reason than to be a lobbying organization in behalf of us, on our behalf in front of Congress and the FCC, if there were nothing else that the ARRL did, that is enough. And membership is $59 a year. People complain because it just went up from 49, and that's the first rate increase that they've had since 2000. People are complaining anyway. So, but it basically allows the national organization, which represents about 1 in 4 to 1 in 5 hams in the United States, to go and basically be our lobbying in front of Congress, so we don't have to do it ourselves. So if you like using the frequencies, that's one of the main reasons that I think ARRL membership is a good thing. So anyway, that's my spiel. That's the last time you'll hear it. And by the way, I've been a member since I was 17 years old, although I have not worked for the ARRL in any capacity until now. So, okay.
They pay you?
Nope. It is an unpaid position. It is a volunteer position. I do it because I want to. Somebody asked me to and said, I think you do a good job at it. I said, you really think so? Yeah. Okay, I'll try it. Okay, now we're going to look at frequency spectrum charts. So we're going to look at the band plan. Band plan, here we go. So notice we have our band plan. This is the national band plan. Everybody can see that. So what frequency is in the 6 meter band? The only way to know what the band edges are is to memorize it. To know that 6 meters covers 50 to 54 megs. There's no other way to do it other than memorize it. You can do that whole thing with 300 and the frequency and the wavelength, but since it's approximate, it's really not going to help. If you look at these answers, notice there's 49 and 52. Well, the 6 meter band, that's 50 megahertz. 49's closer, but 49's the wrong answer. 52 is the right answer. 2 meter band includes 146.52. We can look at the 2 meter band and see that it goes from 144 to 148. Again, the only way to know these things is to memorize them. The technician operator has phone privileges on the 10 meter band. The 10-meter band can be used by a technician from 28.3 to 28.5. We can look at the band and we see phone. It goes from 28.3 to 29.3, but technicians are allowed 28.3 to 28.5. And this is where having the specific band plan really helps, where it's separated out by here we go. It's separated out by operator license class. So this little star right here with the hatches, notice that says novice and technician voice. There you go. So if you don't have a copy of this that you printed out, it's a good idea to have it around. Unfortunately, you can't have it out during your exam, so you have to just memorize it. Where can single sideband be used above 50 megahertz in at least some segment of any band? There's always a single sideband section split out. There are 3 bands where you will find that it has this little red section which says CW and weak signal, no FM, 50.1, 50 to 50.1, and 144 to 144.1, and 222 to 222.34. Those are Morse code only, amazingly. So this is the answer to that. Where it says CW, that means Morse code. So Morse code only in those sections. This other weird band, notice that on the 222 band, it goes 222 to 225 on 1.25 centimeters. 219 to 220, this is a result of the United Parcel Service. Remember I said that there are companies that want to take over frequencies that we presently have because they have another idea, and if they have deep enough pockets, they can get the FCC to say okay through lobbying. This is one of those weird things. We used to have a band that went from 220 to 225 contiguously. UPS came in and said, we have these big brown tablets that we use for package tracking when people sign for their packages. We would like to use those between 220 and 222 because it's not that busy. So what they did is they said, well, we'll give UPS 220 to 222 and you can have 219 to 220, but you can only use it for this weird thing, which is fixed digital message forwarding systems only. So the FCC basically said, how about this deal? We'll take away 2 and we'll give you 1, and you can only use it for a little bit of stuff. Again, another reason why it's important for us to have, lobbying, because otherwise things like that happen.
So UPS and FedEx and Amazon, they all use that?
I think it's just UPS. And
Really?
honestly, I don't know how much they still even use it because there are way more efficient ways to do it now than VHF, but they may have spent enough money that they still use it.
Maybe you should lobby to get it back.
Yeah, it's a lot of work, a lot of money. Let's see, why should you not set your radio to be right at a band edge? Okay, so I'm going to do a little drawing for this. Okay, so here's a band edge. 14.000 to 14.350. Okay, if I select a frequency 14.321 and I do upper sideband, which side of that is my signal going to appear on? The left or the right?
Right side.
Upper sideband, it's going to be over here. Okay, now everything's okay. What if I go over here and I tune my radio to 14.350 and I do upper sideband? Where is my signal going to be? On the left or the right?
Somebody else's space.
That's right. This is the ham band is in this green zone. Outside of this is somebody else's allocation. So if I set this right at the band edge and I'm operating an upper sideband, My radio will let me do it, but I'm operating out of band, and I will hopefully get a volunteer who tells me that, hey, you're out of band before I do it for too long. If you do it for too long, you'll get a nasty gram from the FCC, and nobody wants that. The other reason is that, let's say that your radio is tuned to 14.347. Okay, so that actually is a better situation, right? My upper sideband will be like this. It will end right at the limit. Okay, well, can you think of any situations when it wouldn't end right at the limit? If I suddenly started talking a little bit louder and my signal extended a little bit further, or let's say that my radio warms up and it drifts 1 kilohertz this way, and now my signal is now here. That does happen, especially with older equipment. The other thing is that depending on the equipment that you're using, this could be a frequency counter as opposed to a synthesizer. So when it says 14.347, it's counting a frequency. And what if it's actually 14.348? Well, you think that you're here, but in actuality, you're here and your signal is going out of band.
That means your counter's out of calibration.
Yep. In which case, how would you know unless you know? And the answer is you don't. So typically what we do is we stay a little bit further away from the band edge as a result. So we don't have that kind of thing happen.
Is there a percentage that's a good rule of thumb?
I usually stay a kilohertz away from that, just to be safe. How are U.S. amateurs restricted in segments of bands where we are secondary on the 70 centimeter band? On the 70 centimeter band, notice we go from 420 to 450. We are actually secondary. The military is actually primary there. If you look in on this big chart, you will see that we are sharing the entire band. There we go. Notice that it says radio location right here, and then amateur. That whole area is shared, and we're actually secondary, which means that if somebody else is there, we have to stop using it. Okay.
And how do you tell if somebody's there if you're not broadcasting any intelligent information?
That is a good question. And the answer is somebody may contact you.
Nice.
Yeah. Somebody may contact you and say, hey, you have to stop doing this. Another one that can happen is that a lot of our frequencies are right next to air traffic control frequencies. And if you have a malfunctioning transmitter and you get a notification that says, hey, your signal is putting out a spurious emission that's interfering with air traffic control frequencies, you better fix it. That's not I'll get around to it when I feel like it. That means either turn it off and fix it, or just turn it off and don't use it again. You don't really get too many second chances on that one. Except for some specific regulations, you are allowed, even with a technician license, to transmit at 1500 watts above 30 megahertz. That is a lot of power, and it can cause a lot of harm, which is why it's so important to understand what it is that we're doing. In the HF band segments, which is 80 meters and 40 meters and 15 meters and 10 meters, which we see right here. Notice those hashy marks. There's 80 meters, 40 meters, 15, and 10. You're allowed 200 watts of power, which is actually a lot. License classes. You can get 3 different licenses from the FCC right now. One of which is the technician, another one is a general, and the other one is an amateur extra. No, don't ask me why it's called amateur extra, because I do not know. Why the other ones are called not called amateur technician and amateur general. It's one of those weird things. Technically, it's called the amateur extra. Normal term for an FCC license is 10 years. We don't even get anything on paper anymore. The FCC stopped mailing things out years ago. It's all done electronically. They maintain a database called the FCC ULS, which is the Universal Licensing System. If your license appears as active in the ULS, that means you have a valid amateur license. If you go and create an account, which you will, when you go take a test, you'll have a ULS FRN, which is a FCC registration number. You'll be able to sign in and administer your account and print out an official authorization if you want something for your wall or want something for your wallet. Any one person can have one license. So if you want to have two licenses, you can't do that. If the FCC has you in their database with a license, that means that the license is active and valid. Somebody was asking me yesterday, and I don't think they're here today. Somebody asked me, could they select a call sign of their choice? And the answer is yes, anyone can select a call sign, but no, anyone cannot select any call sign. It has to be in a call sign that is of an appropriate type. So there, for instance, are 1x2 call signs, 1x3, 2x1. That specifies the number of letters, then always one number, one digit, and a number of letters. So in the United States, we have 1x2, 2x1, 2x2, 2x3, 1x3. 2x1s and 1x2s, that would be like NF7Z or N7JI. Those are extra class only. 2x2, depending on where you are, that can be a general class. Usually this is an extra class as well. 2x3s and 1x3s, anybody can select any one of those that's available. Now, there are certain things that are required. The United States has access to all the W's, all the K's, and all the N's, and AA through AL. So notice that 2x2s, these are extra, and these are extra, and all of these are technician and general. The 1x3s and 2x3s. So if you don't like your call sign when it comes out, because you'll be granted a sequentially allocated call sign, and you find that you want to follow, let's say you have the initials XYZ, right? You want to see if W7XYZ is available. If it has not been given to somebody, you could actually request it.
What's the purpose of the different size call signs? Is there a reason for that, or is it just a status thing?
Well, it's part of it is status, but let's say that I am operating and trying to get heard, and my call sign is KJ7ZXP, or my call sign is November 7 Juliet India.
Yeah, one's way easier to say.
Way easier to say. You can sneak it in there a lot easier, and I mean and I do a lot of Morse code. N7JI is a very easy Morse code call. KJ7ZXP is a hideous Morse code call. So, that's why some people, will choose a call sign like, they'll choose W7XYZ. And the reason they would is because X-ray Yankee Zulu doesn't sound bad. But da 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 is a very long call sign. So they're not Morse code operators, because I would never pick that call. But anybody is eligible to apply for a vanity call. Now, once in a while, somebody named Bobby will apply for a call sign like B0BBY. And what does that imply? That implies that they didn't study very hard when they were taking their tests, because the United States does not have access to those call signs. This is actually a Chinese call sign. So you are not able to. And the FCC will send you a nice note that says, this falls outside of the United States. Sorry, we can't do that. And I'm sure that somebody at the FCC office who's receiving this is just laughing their head off, saying, oh, again?
So what happens if you're from China and you have that call sign? You come
Well,
into
you'd
the
have to have
United
it in China.
States.
You'd have to have it in China. I mean, we can't give out call signs for other countries.
Right. What I'm saying is you come to the United States and you transmit on your friend's transmitter. Can you still use that call sign?
It depends it depends if you have a reciprocal license that says so. You can't automatically go to another country and operate.
Oh, really?
No.
Oh, okay.
So we're actually getting to that.
Hey, Scott,
Yeah.
this is Sue. I was the one that asked you the
Yeah,
question
you asked
earlier.
me.
Yeah. And the reason I asked is because I was hoping to get my dad's call sign.
You know what it
It's been
was?
inactive. What? I'm sorry, what?
Do you know what it was?
Yeah, I do. It was KC01FX and it's
It'd be
been,
IFX. It's only one
oh,
number in it,
sorry.
right?
Okay. It's been inactive since 2010. So do they ever reuse those? If I requested it, could I get it?
Okay, so they haven't gotten to the point of recycling sequential call signs. That was a sequential call sign. And so they've never recycled those. If somebody wanted to apply for a call that is unallocated, you can apply for any call that is unallocated that falls within your license class. So if that call sign is free and nobody is, no one's applied for it, you pay your $35 and you fill out the forms and you go through, actually you do it online, and you just apply for that call sign.
Thank you.
KC0IFX. Now, you might actually, my guess is you'll probably have a very easy time getting it. And you said it's unallocated, right? Hey, Sue?
Yeah, I think that unallocated means that it's not active, right? Because
Yeah.
it's inactive. Okay.
Right. So my guess is that you will have no trouble getting that call sign. The reason being that, you think about things that are really, really, special or, like really catchy for some reason. Right. That's a pretty standard run of the mill call sign, and I'm just looking right now. No one's taken it. And my guess is, like, if you wanted to look up K0ABC, if that became available, like the day it became available, somebody would take it. You know what I mean?
Yeah, thank you.
Sounds like
Okay.
there might be some payola going on to get call signs.
No, it's still free, but actually there is believe it or not, there's an art to it, to knowing when to apply. And there are some people who are, who will help, usually for, they'll do it for free. We've got we actually just had somebody in our club just get assigned N7AQ. And the day it became available, the FCC probably got 100 applications for it. And he just won the lottery at that point. Because, I mean, getting a 1x2 call is a pretty rare thing. Okay. Let's see, the grace period for, a technician class call sign. That would be a 2x3. That's a valid technician class call. The grace period for a license is 2 years. After 2 years, it is no longer in its grace period. And within 2 years, you still can't operate, but you can say, oops, I forgot to renew it, and you can renew it and it'll be reinstated. And when does it become able to be used again? As soon as what? As soon as it shows up as active in the FCC database. So basically, once it shows up in the FCC database as active, it's a good call.
So in other words, if they delay for a while, you can't transmit till they undelay.
Correct.
Uh,
You
that's
gotta
fine.
wait. Okay, next, a club station. A club license, 4 people. A club license is 4 people. And interestingly, a club, there's something called an operator license and a station license. So when you get your call sign, you will have an operator license and a station license. Those are 2 separate pieces. The operator license gives you your privileges. The station license says this is for your equipment. So a club call sign has a station license. For instance, we have at South Eugene High School W0AXE, but it has no privileges. It has a call sign, but it has no privileges. So whoever walks into the station, if they want to be the control operator, their privileges become the privileges of that station while they're operating it. If the FCC tries to reach you by email and they can't, they might suspend your license. If you have, if they keep trying to get a hold of you on the 3rd try, they may say, okay, they no longer exist, and they'll just revoke the license. So other places you can transmit from as a US citizen, if you have a US license, you can transmit from anywhere in the United States, unless there's specific reasons that say that you can't. If you're in international waters on a boat that has a US flag on it, because it's an American registered boat, you're allowed to transmit. But the thing is, on a boat, you need to make sure that, because the captain is the captain, you need to make sure that the captain is okay with it. Now, let's see, authorized and prohibited transmissions. When are you allowed to transmit indecent or obscene language? The answer is never. So we basically, it's important to note that we follow the same rules that broadcast television and radio follow. So we're not allowed to transmit obscene language. We can get really big fines, just like they can. There have been some repeat offenders who have been fined $20,000, $25,000, had liens placed against their house, stuff like that.
It's all about the money.
Yep. Well, just
So be
behave.
polite.
That's right. Just behave. Under what conditions are you allowed to transmit music? There's only one. Let's say that you're at a festival or something and you're doing a demonstration and there's music in the background. Probably nobody's going to complain about that. But we are not a service that is designed to transmit music and broadcast music to anyone. The only time that it's allowed to actually be sent as the primary thing that's being sent is during manned spacecraft communications. And this came about when when NASA used to retransmit space shuttle wake-up calls and communications over the amateur waves, over the ham radio band. They used to retransmit all the space shuttle audio. Part of that was wake up, time to wake up. They'd send wake up songs to the astronauts. Those would be retransmitted. So that's why only under space station stuff. When are you allowed to transmit a message that is encoded to obscure its meaning? Let's say that when we consider a space station, that you're controlling a satellite and you want the satellite to do a rotation or to switch on or off. You really don't want somebody else to figure out how to take over your satellite. Or let's say you're doing a remote controlled airplane. You don't want somebody else to take that over. So you're actually allowed to encode something to obscure its meaning. That is the only time. And that's to prevent damage to the equipment, if it's a space station or an RC craft. Now, interestingly, RC craft is weird because that's the only time that you don't actually have to send a call sign identifying your transmitter. So if you have like a radio controlled transmitter for like a drone or something, you don't actually have to send your call sign because it's a radio controlled device. You have to, basically the transmitter, it has to have your name and address and call sign on the transmitter itself. So somebody can always work backwards. When are we allowed to transmit? When are we allowed to talk to other people? Well, basically, we're allowed to talk to anyone in any country who's a ham, whose government says that it's okay to do so. We don't have anyone who said that you can't talk to Americans. They may not have any hams, but there are no countries that have said, who have filed with the ITU, which is a part of the UN, that we're not allowed to talk with them. Apparently, Israel and Yemen are still technically at war, and Yemen does not allow hams in its country, including visitors, to talk with Israelis. This actually came up a couple of years ago when there was the 7 Oscar 6 Tango expedition to Socotra Island, which is owned by Yemen, and they were specifically told, "Hey, we know you're Italians. When you get there, you are not allowed to talk to Israelis because we're still at war with them and we don't allow our hams to talk to Israel." Even though they could hear each other, they weren't allowed to talk. Okay, when can we receive money for doing what we do? The only time you can receive money for doing what we do is if you're a teacher and you're using it for classroom instruction. When are you allowed to sell stuff over the radio? If it's obviously something that is used for radio, like a radio, and you don't do it as a business, you just have it for sale once in a while, you're allowed to announce it for sale and even negotiate a price probably. So basically swap nets. We have swap nets on the air, and that's not a business. It's basically selling, like, a radio or or a computer that's used for a station or something like that. Unless you could say, like, oh, I have a couch for sale, it'd be great in a ham station. That's a little bit iffy. How does the FCC define broadcasting? Broadcasting is for the general public. We don't do broadcasting. We do one-way transmissions and two-way transmissions. So when are we allowed to do broadcasting? Well, it's not really broadcasting. It's one-way transmissions. We're allowed to send code practice. We're allowed to send informational bulletins. Sometimes you'll hear weather reports and things like that. Traffic reports. Broadcasting is intended for the general public. One-way transmissions are intended for hams. So when are we allowed to break the rules and transmit information that supports broadcasters or news gathering or things like that? Well, if I happen to be out of cell phone range and standing next to somebody who's doing a report that is sending information about a dam that's about to break, okay, use it. So there's that immediate safety of life and protection of property. There's those same rules. If those ever show up, that's the right answer. Okay, so what are you allowed to talk about? Communications incidental to the purpose of the amateur service. There are 5 of them, right? All of those 5. So if you're trying to practice learning Morse code, that would be improving your ability as an operator. You're definitely allowed to do that. And remarks of a personal character. Okay, I think this is a great one because I'm now in my 50s. When I was in my teens and 20s, I used to think it was hilarious when I'd get on the air and listen to people talk about the fact that, oh, their back hurts so much and they got a doctor's appointment to go to. And they hope everything's okay. I hope your family's all right. How's your sciatica doing anyway? And I used to think it was really funny. Well, I don't think it's so funny anymore. But those are remarks of a personal character. Control operator, control types. Okay, so control operator is the person who is responsible for operation of a station. There always has to be a control operator present. Okay, so different types of control points. Okay, number one, this is local control. Notice I have my finger on the push to talk button. I am controlling my station. This is actually a station. This is an amateur station I'm holding. I'm controlling it locally. This is local control. If I were to take this and interface this to my computer and then use the internet to go downstairs to another computer, I would be controlling this radio remotely. That's called remote control. That is specifically remote control is control over the internet from a distance. If you're doing that, you still have to be there. You cannot have it just running automatically by itself. And you need to be able to disconnect it if need be. And then there's another mode called automatic control, which is I have set this radio up. It has, let's say, a feature in it that allows me to set it up as a repeater station, where it receives on one frequency and retransmits on another frequency. A lot of mobile radios and even some handheld radios can be set up in automatic mode as repeater stations. One thing they have to do, because it is a unique station, right? This is station equipment. What does it have to do every 10 minutes? And at the end, it has to send out an identification. Has to send out a call sign of this station, of this equipment, which is the owner of the equipment. Not of the people who are using it, but of the equipment itself. Okay, who does the FCC presume to be the control operator of a station? That would be the station licensee. So again, when you get your call sign, there's an operator license and a station license. If it's an individual person, it's assumed that you're going to be responsible for the station. And if the controller operator is not the station licensee, let's say that I have a club station that somebody gave me permission to use, and I go in and it is transmitting some signals that it's not supposed to transmit. Who's responsible? Well, I am, and the owner of the station. Okay, who's accountable if a repeater inadvertently retransmits communications that violate the rules? I'll put this back on the screen. If it violates the rules, that would be, it's an automatic operation. The owner of the repeater is not responsible. The station that's responsible is the one who's doing the cursing into the microphone. Transmitting frequency privileges. Okay, so let's say I have a friend who has a technician class license, and I say, hey, can I come over and use your station? And I'll use my own call sign. Whose privileges are assigned to that then? If I volunteer to be the control operator, they're my privileges. So the control operator's privileges determine where the station can operate. So under normal circumstances, can a technician class licensee be the control operator of a station operating in an extra class band segment? And the answer is no. Now, why does it say under normal circumstances? The answer is because if there's an emergency that involves immediate safety of health, life, or property, those rules don't apply. If you know what you're doing, go ahead and do it. Who can be the control operator of a station communicating through an amateur satellite or space station? If you are allowed to transmit on the uplink frequency, which means basically you're keying your radio to transmit, then you're allowed to do it. Okay, again, control point. This is the control point, the place that the control is achieved from. Remote control, again, is operating over the internet. If you're operating over the internet, the control operator always has to be there and must be at the control point and indirectly manipulates the controls over the internet. This is actually a very popular way of doing things these days. And actually, what's really cool is that there's actually a station in the Cook Islands right now that they basically put together a station on a skid with wheels. They took it on a boat, they pushed it onto the island, put up antennas, and then fired up a satellite communication, a satellite link. And people are controlling the remote station in the Cook Islands on a mostly uninhabited island from wherever they have an internet link from, and operating as that station. So basically, they could be sitting in Maine and operating a station in the Cook Islands, talking to other people in Maine, right across the street, or halfway around the world without actually having to go to the Cook Islands. So that's remote control. Okay, station ID, repeaters, third-party communications. Okay, here we go. You must transmit your call sign every 10 minutes and at the end. Again, note, you don't have to do it at the beginning. This is kind of weird. If you go to Canada, you have to identify at the beginning and the end and every 30 minutes.
Bless you.
Thank you. The rules are different in Canada. When can you transmit without identifying? If you're transmitting to a model craft, such as an RC car, RC plane. When do you have, what language do you use when operating in a phone subband? Phone is a fancy word for voice. Okay, it's telephony. So in the United States, if you're operating in any United States territory or on a US chartered boat, a US registered boat, you have to identify in English. Your whole conversation can be in Spanish or Swahili or any other language you choose, but you have to identify in English. Now, I went to Chile. I got to operate as PE5/N7JI from there. I had conversations that mixed between English and Spanish, but I had to identify in Spanish. All my identification has to be in Spanish. Why do you use phonetics? Phonetics eliminate a lot of ambiguity when you're trying to spell something out. So it's encouraged to use the International Phonetic Alphabet, Alpha, Bravo, Charlie, Delta. Tactical call signs. If you're operating as part of a group that's providing emergency communications or support communications for a public event, such as a road race or a bike race or a foot race or a festival or a carnival or something like that, we're not allowed to get paid for it. We're basically part of the communications support group that's providing emergency communications and health and welfare. So you might be at tactical, you might be at aid station number 6. We recently we provided support for a 100-mile foot race here in Oregon. We also did support for a 200-mile foot race. These are way up in the Cascades, nowhere near any cell coverage. So we basically had about about 25 hams go up there with equipment and provide backbone communications for all of these operations. When you do that, if you're aid station 6, you can identify as aid station 6, but every 10 minutes and at the end, you have to identify with your actual call sign. That's known as a tactical call sign. And it can really help out to say you're aid station number 6, but it doesn't absolve you of the responsibility to identify with your actual call sign. Okay. Let's see. How do you identify a self-identified identifier? Okay. So let's say that we're going to pull up a map right here. And we're going to pull up call sign section. Here we go. Call sign number map. Okay, this is actually kind of cool because we have people here from all over the country, right? So here's the map. Depending on where you live, your call sign will be sequentially allocated based on the number of the area in which you live. So Bear would get a 3 call. Carol, where do you live? You're in Oregon, right? So you'd get a 7 call. Sue, you're in Michigan, right? No. Is it Kansas?
Kansas.
Kansas, you'd get a 0 call. So there was someone else in Michigan. That would be an 8 call. So as you can see, all of these different call signs are assigned to different areas of the country. Now, once you're applying for a vanity call sign, you can apply for any call sign number that is part of the continental United States. Like if I lived in Oregon, I couldn't apply for a Puerto Rico call, but I could apply for a 9 call. It used to be that whenever you moved and you reported a new address to the FCC, you actually had to get a new call sign.
Right, that's why my dad said he had a
Yeah.
couple of numbers.
Yeah, it kind of destroyed the continuity, of having the same call sign forever. Let me make sure this is up. There we go. There's the map. So if you live in 3 land, as we call it, you get a 3 call. New York, New Jersey would get a 2. Maine would get a 1. If you're in the Southeast, you get a 4. Kansas would get a 0. If you live anywhere in the West except California, you get a 7 call.
And that is which number is that?
For what?
You say it's a 3, that's only 1 digit.
Well, I mean, that would be the number in your call sign. So you'd get like a KC3 something. Or something to that effect. KD3 something. That would be
So everything else is a letter.
Everything else a letter.
Okay.
So it's letter, number, letter. 1 digit max. Okay, so those are the numbers that you would get. But again, once again, like my wife, we live in Oregon and she has a 3 call. One of the other girls in the or one of the other ladies at the U of O club, she lives in Virginia. She's going to school in Oregon, and Virginia is in 4 land, and she has a 3 call.
Why is California got to be different?
Because California has 45 million people. So they have their own number all to themselves. And they are still blowing through it faster than almost anybody else.
Was that because half the people think they're going to fall off the shelf?
No. I mean, it's just about like, if you look at where the different numbers are,
Yeah.
like Oregon, we're up to the KK7s. California is up to the KN6s. So in the 4 land, they're up to KQ4s. Maryland's up to, I think, KC3s. So the population is smaller. Maine, I think, in 1 land, they're up to KC1s. So different areas of the country have progressed at different rates based on population and based on new licensees.
So what do they do when you get your general class license? Do they just drop a digit off or something, or
you have a choice. Yeah. You could choose to get a different call sign. It'll be the same number of letters and numbers, but no, you can't drop anything off because there's a good chance that somebody already has what you have if you dropped a letter off. So it used to be a long time ago that you would get a WN or a KN or a KW or a WB, and they would just drop a letter from it. Now it's that you keep the call unless you request a new one. And at any time you upgrade, you can request a new one if you really want. All right, third-party communications. Oh, self-assigned indicators. Okay, so N7JI, now that we showed those numbers, if I'm operating in Texas, I would operate as N7JI/5. I could also be portable 5, I could be stroke 5, I could be slant 5. Those are just a couple of different ways to say, there's a slash mark. Third-party communications. We do this at the museum all the time. Anytime you have a friend who's not licensed and you want to give them the experience of getting on the air, using your call sign, they are a third party to the communication. Now, they could also somebody hand you a message and say, Joe wants pepperoni pizza. That would be third party too, because it's basically any message, whether it's being sent on behalf of another person or being spoken by that individual person on behalf of another person. So we could do third party to third party. Like we could have two different museum stations with licensed hams and two 5-year-olds talking to each other. They would both be third party. We are allowed to do that in the US and Canada, and between the US and any other country that permits it. There's a big list of them, but you have to check it before you do it. And last but not least, if the FCC knocks on your door and wants to inspect your station, they're the ones who give you the license. You have to let them in to look at your equipment. I've never had this happen. I don't personally know anyone who's ever had this happen. I know of people who've had this happen. Usually there's a pretty strong case before they ever do anything like that. All
And
right.
they do that. Why? Because you're transmitting spurious emissions and crap like that.
And potentially interfering with something really important, like air traffic control. That'd be a really good way to raise somebody's ire.
So we got Patuxent River Naval Air Station out here, right?
Yep.
They interfere with everybody's stuff and they don't care.
They don't care. Well, and they don't have to.
Government, they don't care.
Right. They don't have to. They do come first. Now, depending on what they're doing, it might be that somebody could complain and actually get somewhere, but what they're doing is basically in the support of national defense. So good luck.
Yep, pretty much.
Yeah. Well, that's it for me.
Are we done?
We're done.
No.
It's 1:00. We're done. We went through the whole thing.
No, it's 4.
Well, it's 4:00 there. Yeah. So, all right. Does anybody have any questions or comments or anything else that they want to hear more about? Anything else that they need clarified?
So I'm
Hey,
going to be
Scott, I
signing off.
just
Scott,
want-
just wanted to say thank you.
My pleasure.
Thank you for holding this class.
My pleasure. And Scott,
Yeah, I just want to echo what Howard said. Thanks. I greatly appreciate all the time and energy and effort you did. It really helped me understand this more.
Yes.
Thank
so-
you.
Go ahead.
I just said thank you.
Oh, yeah. So, okay. So here's the other thing. Very briefly, let's talk about exams. All right. So if you go to, oh, I didn't mean to do that. Hold on. I meant to go to, okay. I meant to go to Cam Study Exam Finder. Find an exam session. Okay. There are a couple of different resources that are out there. And like I said, normally what we would be doing right now is I'd be calling people in half an hour and say, it's time for your test. So, but being that this is a holiday weekend, we wanted to give all the examiners that I normally work for a little bit of time off. So notice that there are none today, but look at that, even tomorrow. Las Vegas, you could select remote. And look at that. There are actually exams that are being given today. Actually, quite a few of them. There are a lot of exams that are being given tomorrow. A lot of exams Tuesday, a lot of exams Wednesday. You basically sign up for a time slot and do what they say and, apply for an FRN with the FCC and go take your test. Now, notice we also have the way that this is set up. Notice these things that are called VECs. Right. Okay. So I work with the Anchorage VEC, and notice they've got lots of different choices. They say we're always available. I know these are a really good bunch of people because I work with them all the time. ARRL is part of the ARRL, but notice it says VEC. There are 14 volunteer examiner coordinators who get together and work with the FCC to create the question pools and set up administrative procedures for administering exams. Notice that there are a lot of them. There may be some that typically most charge between $5 and $15. Most of them charge $15. There are still some that give them for free. I think Laurel still gives it for free. I don't think, yeah, they don't do any remote exams, but they do a lot of in-person exams. Not necessarily in Laurel, Maryland, but in other places. So here's
That's where
MoCam.
it's at, is Laurel, Maryland.
No, that's where they're based. That's the name of the group.
Oh, okay.
So notice
That's what
there are,
Charlie said something about going to Annapolis and taking the test up there.
yeah, I mean, I don't know who it is, but GLARG is the Greater Los Angeles Amateur Radio Group. And again, there are lots and lots of choices. They're $10. So you have lots and lots of choices. Now, I will say also that if you want to take an in-person exam, and there are a lot of them listed. Let's see, September 8th. So interestingly, the one that I work with is not even listed here. It's an ARRL group. And it's on Friday. We're not even listed in here. It's the Valley Radio Club in Oregon. We're giving an exam next Friday. So what I would recommend doing is when it comes time to studying whatever you're going to study for, if it's technician, if it's a technician and general, whatever it is, just brush up on the whole question pool to the point where you're getting at least 85% on every test. You can take an infinite number of practice tests. There's, you know, it's always free to do. And you can take one every hour for a week if you really want to the point where you've seen every question 50 times. So, you know, don't feel bad about doing that. There are a lot of people who do that, you know, who really work at this, and they want to go in and knock out as much as they can in one setting. I know people, I've met a good number of people, one of whom goes to Portland State, actually, who started at nothing, and he crushed all 3 exams in one sitting. He said, well, you know, I figured I'm an engineering student. I should be able to do this. So I just studied them all and went in and passed technician, general, and extra in one sitting.
And that takes how long?
As long as it takes you.
No, I mean, how long do they give you? So let's say
As long as you need. Nobody's in a hurry. That brings up a fun story that of my life. I've been an examiner since I was 18. And I used to give all the exams at the University of Maryland. And one of the people who came in for the exam, he ended up, I think, NQ3X. And he was almost blind, but insisted on not having the exams read to him because he was almost blind. So he had these really thick glasses and a magnifier, and it was all on paper. And we started at 8 o'clock. We had 3 people there giving exams and 3 people taking exams. The other 2 people taking exams, they were done in 20 minutes and out the door. Right? Like, oh, this is going to be an easy day. So after about 45 minutes, well, okay, he passed his 20 word a minute code test, blew through that like it was nothing. So then it's on to written exams. Took him 45 minutes to pass his novice. Took him 45 minutes to pass his technician, because he's looking like this, reading through every question. We were there until 3 o'clock that afternoon. So when I say, you know, we're gonna give you as much time as you need, we're gonna give you as much time as you need. But we were there for like 7 hours.
And that's because y'all are volunteers and not constrained by somebody who's paying you.
That's right.
All right.
That's right.
Gotcha. So I think I'd be better off taking one somewhere rather than at home, because I just got too much clutter. And I was looking at some of the stuff, and they say you got to go in the bathroom and take
it basically has to be like a sterile space.
All
so
right.
the bathroom works really well.
I don't have one. I go outside, do it.
Yeah. Hi, Nate. Almost done. So here's another one that I would like to bring up, which is ARRL find an exam session. This is specifically with URL, but so give me a zip code.
20657.
Let's see.
Oh, okay.
Okay, let's just look up all of Maryland.
Oh, you couldn't find it?
Well, I mean, it's not specifically to that zip code. I don't know how close it gets.
20619's in
Here we
California.
go. Hagerstown, Catonsville, Davidsonville, Fort Washington's not that close. There's one in Laurel, Rising Sun, that's up north, Severna Park. That's Annapolis.
All right.
So yeah, this is basically everything in Maryland for the next, 6 months.
So either way, you can go with that, or you can go with the ham study people. Either way, it gives you
Yeah.
the same results because it's basically the same people, right?
And this is specifically the ARRL. And again, there are, depending on whether or not other VECs schedule even through them is another story. I mean, there are so many exams available these days that it's almost embarrassing.
So should I study for general class as well and just do
Kind of up
both?
to you. It's kind of up to you.
I mean, it's not that much harder, is it?
Not really. I mean, it's about learning. The theory is mostly the same. It's
Right.
about specific band edges and requirements. I mean, I wouldn't tell. I mean, a lot of it depends on your background and again your experience. So just look at it and see how it looks.
Gotcha.
What, Nate? Yeah. What do you need? You need to go somewhere? Where? I'm gonna have to play chauffeur soon.
Oh, yay.
Yeah. All right. Any other questions?
Yeah, I have a quick question for you.
Yes.
Before we get our equipment, is there a website we can go to just listen in on transmissions and kind of get a feel for it?
Yeah. I mean, that same thing that I was using. Let me see if I still have it open.
The SDR thing?
Yeah. Well, okay. So if you go to, I'm going to go to websdr.org, but not specifically this one. We're going to go to websdr.org. This is like a clearinghouse of software defined radios that are all over the world.
Oh, wow.
There's a lot of them. I just happen to really like the University of Twente. Notice it shows up as #1. I really like their website. I really like their SDR, but notice it's also Northern Utah, and they have yellow, blue, green, magenta, teal, and you can pick any one of those. And okay, so let's pick green, 20 meters. Can you hear it?
I can, yeah.
Yep. So, I mean, this is an incredible thing.
WA5 Victor Alpha 9 Victor India.
You can play with the filtering. Okay, K1 VMT. Hey, Allie. I know you said you were interested in Morse code, right?
Yeah, I was gonna ask about that. So I have some auditory processing issues and have a difficult time like hearing things quickly. So how does the Morse code test work? Like, do you have to?
Well, when you say test, I mean there's no exam or anything.
Oh,
anymore.
I see. Okay.
Yeah, that hasn't happened. It hasn't existed for years.
I see. I can
I
write and read Morse code just fine, but I have a really hard time hearing it and interpreting it. I think I need to practice more, but that's difficult for me.
well, KA6BIM. W4 SSF was there.
I can't make any sense of that.
So when you say, well, more, and so how are you at languages?
Languages?
Yeah.
Well, I only know English. I took a Japanese class briefly in high school. I'm good with visual stuff, but
Okay.
my hearing's fine. I just have a hard time sometimes processing auditory information.
Okay. So, I mean, really, it just comes down to this comes down to a training of your ear to, you know, to recognize certain things. Like,
Mhm.
so let me WF7T. Like I said, I've been doing this for
Uh-huh.
almost 40 years. I can go pretty fast, but so here's another something or other, this thing called Morse key.
Mhm.
It's an app on the phone.
Uh-huh.
And let me make sure I have original sound for musicians. Can it tell me if you can hear this?
Mhm. That's yeah.
Okay, so I'm going to set this up for a straight key. Okay. Okay, here we go. Can you hear a tone?
Yeah, definitely.
Okay. All right, so this is a letter A.
Mhm.
Did you recognize that as an A or not?
Yeah, I have to kind of visualize it in my head. Like I spent a lot of time writing notes to myself in Morse code or binary or
Okay.
other things visually, but I'm not used to yet hearing it and then translating it.
Yeah. And because I teach Morse code, and one of the things that I teach is going straight from this to being an A. And
Mhm.
it's the same way if I say the letter A, you don't have, I mean, do you see a letter A or you just know that that's a letter A?
Kind
Like
of
if,
both. I don't know.
I
Yeah.
mean, like if I say C,
Uh-huh.
you know that's a letter C. You don't have to
Right.
like write it down and say, oh, it's a
Mhm.
C, right? So if I send this,
Mhm.
eventually what happens is that just becomes a letter C,
Mhm.
as opposed to it representing anything visually or anything like that.
Right.
So that's, you know, that's just a case of practicing. And
Mhm.
so
So
that,
is that app like can you write things in and then like practice
not this
interpreting
one,
things?
not
Okay.
this one. But if you want to learn that, what I can do is, give me 1 second. Okay, let's see. It's this one right here. Okay, lcwo.net. Learn CW online. And this is one of the things that I use for teaching code. This actually has a portion of it. Let me see if I can remember my password. Please be my password. Hey, it worked. Good. Okay. All right. So convert text to Morse code.
Oh, fantastic.
Right. Now, this thing also has something in it called Morse Machine, which is a wonderful little device. If I can remember where to find it. Morse Machine. There we go. All right. So I'm going to select custom characters and
Hey Scott, I apologize for cutting in, but I have to go to work.
Yep.
Thank you so much for everything. I really appreciate it.
Thank you again. And if you have any questions or anything, let me know.
Okay.
And let me know
Thank
when
you
you
so
pass an
much.
exam.
All right. Bye-bye.
And okay, so here we go. CW settings. So notice all the letters are selected,
Mhm.
right? If I want, I can just say, okay, let's clear them all. We're just going to start with a couple of basic ones. We're going to start with a T. And we're going to start with, sorry, this is saying we're going to start with an E. There's an
Mhm.
E. So you basically create an account and you say, okay, well, we're going to start with, we'll leave an N and the A there just for fun. And we're going to submit, save our changes. Okay. Now we go to Morse machine and ENANT. Ready? Here we go. Here we go.
N
That's an N.
E.
T.
That was, I think A.
Yep.
That's really here. I'm gonna
That's
turn
it.
my. Yeah, that was an A again.
Yep.
Okay. T.
That's a T.
E. A.
Yep.
T.
And
Okay.
it'll just do this forever. And the nice thing is now, okay, you're good with those. You can go back to your settings and you can just add letters as you go.
Yeah.
Okay.
And
That's really helpful.
And if you get one wrong, for instance, ready? It says you did it wrong and it makes you do it again.
It bonks you.
It bonks you in the head. Yeah. So
Awesome.
great little website.
Okay, fantastic. I'll write that down.
lcwo.net.
Great.
But is that a free service or do you have to?
It's free.
It's free.
Yep.
Wonderful.
You set up an account and it's free. All right. I got to go give a kid a ride.
Thank you so much for everything.
Thanks, everybody.
Thank you for doing this.
Yeah, thank you, Scott.
Good to
Appreciate
meet
it.
you all.
And yeah, and if you have any questions, let me know. And as soon as I have this